We thought we understood black holes. Gigantic, invisible monsters that lurk in the dark, devouring stars, warping time, and swallowing everything, even light. But what if we told you that nearly everything you've heard is just the surface? That the real story begins after you fall in? Black holes aren't just empty voids. They're the most complex, mind-bending objects in the known universe, where space stretches, time shatters, and the laws of physics begin to whisper secrets they don't reveal anywhere else. This journey isn't for the faint-hearted. We'll dive into firewalls that may incinerate you before you cross the threshold, time loops where past and future blur, horizons made of holographic information, and singularities that might not even exist. Inside, space could spin like a tornado, time might run backward, and echoes of quantum chaos might ripple outward like cosmic heartbeats. Some theories say you'll never truly reach the center, others say you'll birth a new universe on the way down, and still others suggest you'll see your own past, or become a ghost of information painted on the surface. These are not metaphors. These are real possibilities based on our best physics. So fasten your mind, not your seatbelt, because this is a fall with no end into the strangest corners of the cosmos. Welcome to the black hole. The event horizon isn't the real boundary. Most of the time, when we hear the word black hole, we think of a cosmic trapdoor that leads to nothingness, so-called point of no return, where even light is doomed to disappear, is in the middle of that picture. A lot of people describe it as a sharp edge, the very edge of gravity's grasp. But this is a lie, one that is shaped more by our narrow view than by the truth of the universe, because there is no wall at the event horizon. It's not a top. The line isn't even always there. It's just a math trick, a moving ghost line that looks different depending on where you are. If you are far away and looking, it looks like things falling toward a black hole slow down as they get closer to the event horizon. This happens because of very strong gravitational time delay. The picture of the item stretches, reddens, and fades until it stops moving at the edge and never quite crosses it. You wouldn't feel anything special at the horizon, though, if you were the one falling in. Not a bump, not a warning. You wouldn't have any trouble getting through. The journey goes on for you. That paradox is at the heart of general relativity. It's also where black holes start to make us question our most basic ideas about space, time, and even observation itself. For this strange reason, scientists say the event horizon is observer-dependent. It looks like the end of the road from far away. It's just another part of the journey when you're close to it. It's like the sky on Earth. When you look across the ocean, it looks like a line, but when you try to sail to it, it keeps getting farther away. The event horizon of a black hole does something similar, but this time it's space-time that changes shape. This isn't just a strange quirk of physics, though. It has very bad effects. Take Stephen Hawking's famous guess that black holes give off energy. The theory of quantum physics says that pairs of particles are always coming and going. One of these particles might fall in near the event horizon, while the other one gets away. What we see from the outside makes it look like the black hole is slowly going away. It seems that the event horizon might not be as solid as Einstein thought because of this process called Hawking radiation. It would change the rules of thermodynamics, conservation, and maybe even quantum information by itself. If information leaks out via Hawking radiation, we face the so-called information paradox. Does the black hole eventually erase the identity of everything it consumes? Or does the information somehow survive, encoded in radiation or the event horizon itself? Quantum physics demands that information cannot be destroyed, but black holes seem to challenge that principle. And here's where things start to spiral. If the event horizon is just an illusion, or worse, if it doesn't exist at all in a stable form, then we may be misunderstanding the black hole entirely. Some physicists think the event horizon might hide a violent secret, the firewall. This radical idea proposes that instead of a smooth ride past the horizon, you'd hit a wall of high-energy particles, a quantum inferno that obliterates you instantly. This would protect quantum rules, at the cost of destroying general relativity's gentle transition through the horizon. It's one of the most hotly debated concepts in modern physics, and no one has found definitive proof for or against it. If the firewall exists, our mental picture of falling into a black hole, calm at first, chaotic later, gets flipped on its head. Also, let's not forget about black holes that spin. The event horizon is changed by these Kerr black holes into a strange shape, a spinning oblate region with an outer shell called the ergosphere. As the black hole spins, it pulls space along with it in this spinning area. Being still isn't enough. You have to move to stay still. The event horizon is now a part of a bigger, more complicated dance between gravity, mass, and angular momentum. Yet even from this point of view, the idea of the sky as a clear line keeps falling apart. Deep inside the black hole, past the event horizon and even the whirling whirlpool of the ergosphere, is the singularity. This is the supposed point where density is infinite and our laws of physics stop working. However, the event horizon is what keeps us out of this realm, and we need to understand it in order to see the secrets that are hidden inside. But everything points to it not being a gate at all. It's just a projection, a mirage that was made by gravity itself in the sky. Firewall paradox. Will you burn or float? As you move toward a black hole, the world behind you seems to stretch and fade. The event line is crossed, and then there is nothing. There was no jolt, flash, or sounds from space. Nothing but quiet darkness. Based on general relativity, that's what should happen. Einstein said that the event horizon is nothing more than a spatial illusion, like a line on a map. A group of scientists, including Almheri, Marolf, Polkinski, and Sully, AMPS, dropped a surprise in 2012 that broke this calm picture. The idea they put forward sent shockwaves through the field of theoretical physics. The event horizon might not be smooth at all. It could be a wall of fire. This is the heart of the firewall paradox, a clash between three ideas that seem to be true individually but cannot coexist. First, general relativity says that crossing the event horizon should be uneventful for an infalling observer, no drama, no incineration. Second, quantum mechanics insists that information cannot be destroyed. And third, something called the monogamy of entanglement suggests that quantum information can't be perfectly copied or shared between multiple systems. But when you combine these principles in the context of a black hole, they collide violently. It sends out Hawking radiation in pairs when it's a black hole. One particle goes in and the other one gets out. To keep quantum coherence, the particle that is leaving must be connected with its twin inside in some way. You're breaking the rules, though, if you also say that this escape particle is mixed up with earlier radiation so that no data is lost. The reason for this is that quantum particles can only be fully connected to one system at a time. It's time for something to give. What's going on? The AMPS group suggested that at the event horizon, we give up the smoothness of space-time. In other words, the horizon is not a smooth fall, but a wall of fire that burns anything that meets it. As soon as you hit the edge in this model, all bets are off. That's not what you do. You burn in place. The picture is shocking, and it goes against Einstein's ideas. It does, however, protect the privacy of quantum information, which is a very important thing. The information isn't lost in the barrier model. It's violently sent out in a burst of heat and radiation. The firewall cuts through the paradox like a cosmic machine, making the edge of the black hole very firm. Many physicists argue that firewalls are a symptom of our incomplete understanding rather than a true solution. They say the paradox points to the need for a new, deeper theory, one that fully unites general relativity and quantum mechanics. Others propose exotic alternatives. For instance, the Fuzzball theory emerging from string theory suggests that black holes are actually tangled balls of strings with no event horizon in the traditional sense. In this view, there's no firewall, because there's no clean boundary to begin with. The surface of the black hole is just a chaotic mess of vibrating quantum information. Then there's the ER=EPR conjecture, a wild idea proposed by Leonard Susskind and Juan Maldacena. It posits that entangled particles, EPR pairs, are connected by microscopic wormholes, Einstein-Rosen bridges. If true, this could explain how information escapes from black holes without violating quantum rules, and without resorting to a fiery demise at the horizon. But this theory is still in its infancy, and its implications are barely understood. As of now, black hole shields are still one of the most controversial topics in modern physics. Einstein and quantum theory are at odds with each other. There is still no sign of a peace deal. But even so, this cosmic puzzle has a very human feel to it. The firewall paradox doesn't just make us question math, it also makes us question what we think we know. It makes us think, what would really happen if you fell into a black hole? It could be a quiet fall into darkness, or a quick, dramatic death right at the edge. Ergosphere, where space itself spins. Think of a storm. Now picture something that is spinning that isn't air, but space itself. So it is around a rotating black hole, which is called a Kerr black hole, after the New Zealand mathematician Roy Kerr, who in 1963 solved Einstein's equations for spinning singularities. In early physics thought experiments, black holes were thought to be simple and static, but in real life, black holes probably rotate. The fabric of space-time around them changes in a very interesting way when they do. The ergosphere is an area outside the event horizon where space bends so strongly that nothing can stay still, not even light. If you try to stay still in this area in relation to the black hole, it will pull you along with it as it spins. Time and space are being spun like cotton candy, so it's not just gravity pulling you. Frame moving is the term for this, and it's not just an idea. Satellites like Gravity Probe B have confirmed it around Earth. But it gets infinitely worse when you're near a spinning black hole. The ergosphere is shaped like a peanut or a football that has been flattened. It bulges outward at the equator because of the centrifugal force of spinning. Technically, you can still get out of this area, unlike inside the event horizon, but it takes a lot of energy. The ergosphere has some strange qualities that make it a place where physics bends so hard that it snaps back with energy. This is where things get really crazy. This brings us to the Penrose process, which is one of the strangest ideas in black hole science. Proposed by mathematician Roger Penrose in 1969, this theoretical mechanism suggests that it's possible to extract energy from a rotating black hole using the ergosphere. Imagine sending a spaceship into the ergosphere. Right before it gets swallowed up, the craft splits into two parts. One half falls into the black hole, the other escapes. But here's the twist. Due to the way space-time is warped, the part that falls in has negative energy from the black hole's perspective. As a result, the escaping part actually carries away more energy than the ship originally had. In essence, the black hole slows its spin just a little, and you get to ride off with a cosmic energy bonus. Some scientists think that the amazing jets that shoot out from active galactic centers may be powered by this very idea. Some of the most powerful things in the world are these jets, which can reach millions of light years into space. A lot of people think that they are moved by bent magnetic fields in the ergosphere that shoot charged particles into space like a cosmic missile. It's about powers that are millions of times stronger than what the Large Hadron Collider can make. The ergosphere isn't just about power, though. It's also about how you see things. Things like time, light, and cause and effect act differently here. There are strange turns and bends in light tracks. If you tried to shine a laser straight on, it would wind around and around. Objects could revolve backward in time compared to people far away. You might even be able to see things happen in strange ways, like seeing the end before the beginning. Let's talk about spin now. A black hole's spin parameter is a number between 0, no spin, and 1, highest spin, that tells us how much it spins. It's possible that most black holes are in the middle, but some may spin dangerously close to the edge, and the ergosphere gets bigger, more energetic, and more twisted as that number gets closer to 1. If a black hole were to spin very fast, the line between the ergosphere and the event horizon would be so fuzzy that the two might almost touch, opening a way into the world with the most extreme space-time bending that is known. The scary part is that you wouldn't even feel it. You might not notice anything right away if you fell into the ergosphere. Not a blast. There was no light flash, but you would start to spin slowly. It was bound to happen. No, not by choice. There is an unchangeable rule in the ergosphere that says nothing can stay still. There would be more pull on you than just gravity. The world around you would be spinning. Your path would be taken away from you like a leaf caught in a whirlpool. The inside-out black hole hypothesis. What if going into a black hole doesn't destroy you, but turns you inside out? The inside-out black hole hypothesis is one of the most strange ideas in modern theoretical physics. It is based on this strange thought. Not many people agree with it. It hasn't even been fully established yet. In the minds of theory researchers and cutting-edge scientists, though, it's a real thought experiment that could change everything we think we know about the universe and ourselves. Most of the time, the story goes that the singularity is in the middle of a black hole, a place where space-time bends all the way to infinity. The laws of physics don't work where density is endless and volume is zero. But a lot of scientists don't really believe in that kind of singularity. A lot of the time, infinity is a red flag in science. There's a sign that says, our math broke down. There must be something more going on. Something like a topological reversal could be that something. In simple terms, this means that the inside of a black hole might be the opposite of what we know about space-time. Not just in a flip-the-mirror way, but in a deeper, more structured way. Think of a Mobius strip, which is a one-sided surface that makes you face the wrong way without you realizing it. Take a look at a Klein bottle, which is a 3D shape that can be turned inside out without breaking. These are mathematical models of surfaces that can't be oriented. Some thinkers think black holes might work in a similar way, as machines that flip space and time. This idea says that when something goes into a black hole, it doesn't get squished into a single point. Yes, it's squished. It has changed. Then, as it goes through the so-called singularity, it re-expands, but not into our universe. Instead, it goes into a mirror domain that is the exact opposite of our universe in terms of geometry. There is a cosmic negative inside the black hole, where time, space, and maybe even the rules of physics act in different or switched around ways. This might help explain one of the strangest problems in general relativity. The equations don't say you can't go through the singularity, they just stop being defined at a certain point. You could make the equations longer if you could make that point more regular in some way, like by adding quantum gravity changes or using higher dimensional topology. What do those extra parts show? That the way keeps going. It keeps going. Into a different area. Into a different time. In some ways of looking at it, each black hole in our universe might be the beginning of a new universe. Each black hole gives birth to new dimensions in its heart, making reality look like a Russian nesting doll. This idea is sometimes called black hole cosmology. It's just a guess, but it seems like a great way to answer one of the most important questions in the world. Where did our universe come from? Things that used to be in the center are now on the edges, and things that used to be on the edges are now in the middle. In a new universe, the singularity is the start of time, and our event horizon is the Big Bang of that universe. Everything inside the black hole is space-time that is being squeezed together and moving away from the center. This is similar to how our universe is growing after the Big Bang. Not only are the locations wrong, but so are the path, the entropy, and the cause. Now, imagine for a moment that you're falling into such a black hole. As you pass the event horizon, your perception of space warps. Your sense of time begins to twist. You feel crushed, but not destroyed. And then, as you approach the center, something else happens. You flip. Like stepping through a looking glass, your trajectory in time continues, but the arrow of space reverses. From your point of view, you're still falling. But in the new inverted universe, you've just been born. You are now expanding outward from what the new inhabitants might call their singularity. You're no longer part of the old universe. You are part of the new. If black holes make new universes, is ours just the inside of one of those collapses? Are the laws of physics in our universe the mark of a dying star on a bigger reality? And can any of this ever be tested? Most likely not. These theories are very close to being able to be seen. Beyond the event horizon, there is no way for a probe to come back. Because the shape is backwards, no information can get out, but math can sometimes see things that light can't. The thing it finds is not destruction, but change. Frozen stars, what distant observers really see. Even though people talk a lot about event horizons, spaghettification, and infinite gravity, the truth is much stranger for someone looking from a safe distance in space. Based on Einstein's math, it looks like nothing goes into a black hole. Not really, not all the way. Matter seems to freeze right at the edge instead, put on hold, not moving, always. This strange illusion is caused by something called gravitational time dilation. When compared to places with lighter gravity, places with greater gravity see time move more slowly. The gravity pull is so strong near the event horizon of a black hole, the point of no return, that time seems to slow down to a crawl. Let's say a pilot is falling into a black hole. The closer they get to the event horizon, the longer it takes for their signals, light, radio waves, and anything else, to reach you from far away. Every second of their fall is stretched out over hours, days, and minutes. Their heartbeat, their words, and their movements were all slowed down, moved, and smeared across time. They seem to stop in the end. There it is, being close to the event line but not quite crossing it. Yes, they fade. They get dim. Their light gets more and more redshifted until it falls completely below the visible spectrum. They never go away though. From your point of view, they're always falling, but they never get there. Even after 1 billion years, the last photon from their fall would still be slowly making its way toward your camera, as if it were stuck in space mud. This is where the phrase "frozen star" comes from. You don't see the black hole as a hole at all. You see it as the ghost of something that fell to make it. A shell of the original star that has been frozen at the point of no return. However, the story changes for each viewer. To the falling astronaut, everything feels normal. They pass through the event horizon without fanfare, without fireworks. They might not even realize they've crossed the line, because locally physics behaves as usual. No sudden wall, no burn, just continued freefall into a deepening abyss. One of the strangest effects of relativity is this difference between what you see from the outside and what you feel from the inside. It's not just a puzzle of ideas, it's a line between two totally different worlds, a causal split. It gets stranger. Because the same thing that makes this freezing appearance happen also has strange effects on light and radiation. Gravitational redshift means that photons sent out from just above the event horizon lose energy as they travel farther away. That's the reason black holes look dark. No, there is nothing going on at the edge. Anything that tries to get out loses energy as it climbs out. It's like the black hole eats the speed of light before it gets to you. But we might still see the ghost of what was. Stars that collapse, falling matter, and even whole gas clouds can leave behind weak marks close to the horizon. These marks are like gravity holograms that are always visible just outside the void. Astronomers have been arguing for a long time about what this means for how black holes form. We only see stars getting closer to the event horizon as they slow down to infinity. When does the black hole actually form? Can we pick a point in time and say, that's when it turned into a black hole? The answer is, it depends on how you look at it. The black hole forms in real time as the matter falls apart. It is smashed to pieces by gravity. You, on the other hand, see the process as never really ending. The edge never completely seals shut, it only gets close. From your point of view, the black hole's birth will never happen. This is one reason why some scientists don't believe in event boundaries at all. What if they don't really form? Could it be that the black hole is just a growing illusion? From afar, it might look like a singularity, but it never really becomes one. This leads to different models. such as the Firewall or Fuzzball models, which try to make quantum physics and general relativity work together by getting rid of or changing the standard event horizon. In these models, the frozen star isn't a dead body, it's a quantum froth, a wall on fire, or a mess of strings that acts a lot like a black hole but doesn't have any problems. From a realistic point of view, though, the frozen star effect still wins. From remains of stars with a lot of mass to supermassive giants at the centers of galaxies, every black hole we've seen acts like it has an event horizon, a range beyond which the sound doesn't come back. And everything we know about light curves, radiation patterns, and how accretion disks behave is a scary match for Einstein's forecasts. Time dilation to infinity. Time here on Earth feels like a steady beat, like a clock ticking that moves the world forward. Time doesn't just bend near a black hole, though. It gets stretched and twisted until it finally breaks. You're not just going through space as you fall toward a black hole's event horizon. There is a lot of gravity in space-time, which changes not only your path, but also the flow of time around you. If you look at the time from far away, it seems to move faster as you get closer to the horizon. At first, it seems subtle. Your heartbeat feels normal. Your watch ticks on. But from the perspective of someone outside the gravitational well, say, a friend watching you fall, your actions appear to slow. 1 second for you might be 2 for them, then 10, then 1,000. And eventually, your time becomes frozen compared to theirs. This isn't just theoretical. It's a direct prediction of Einstein's general relativity. Time dilation occurs anywhere gravity is strong, but nowhere is it more extreme than near the event horizon. There, the pull of the black hole slows down local time so dramatically that from the outside, it appears you take forever to fall in. Say you say goodbye with a wave as you go down. Your friend will feel that wave, but with each flick of your wrist, it will move more slowly until the wave itself is redshifted into nothingness. From their point of view, you just stand there, moving so slowly that it looks like you stopped in the air. But from your point of view, time keeps going as usual. You would feel like you were going normally, but faster and faster as you got closer to the event horizon. As you crossed it, you wouldn't notice anything out of the ordinary because physics doesn't stop at the edge. Not you, but space outside is moving faster. You just keep falling deeper into the gravity hole. The world outside starts to speed up in time as soon as you cross the event horizon. In your last moments, you could see galaxies change, stars die, and whole societies rise and fall. Light from billions of years of development in the universe rushes toward you in a single bright crescendo. The black hole is now like a time machine, but it doesn't move you forward or backward in time. Instead, it lets you see the whole future of the universe happen in an instant. It's not made-up science fiction, it's just the structure of space-time. The deeper you fall, the faster the universe outside appears to move. By the time you're nearing the singularity, the rest of the cosmos may have already experienced its heat death, where every star has burned out and every atom has dissolved into background radiation. And yet for you, it's only been a few minutes. This concept, infinite time dilation, forces us to rethink what death even means inside a black hole. For most physical processes, the end is a clear boundary, but here it's a gradient, a blur, a passage through which your personal time becomes disconnected from the timeline of the rest of existence. This brings up one of the strangest possible questions in modern physics. What if someone fell into a black hole and saw the world end? There are some ideas that say yes. As the viewer falls, they might feel everything that happened in the world during a big freeze, a big rip, or even a phase transition collapse. But would they be able to get it, or even handle it? That depends on how well their mind can handle changes in gravity, stress, and the tides that are at play. But science doesn't say that someone couldn't see the future when they are falling, at least in theory. If black holes disappear because of Hawking radiation, then a person falling into them might never even get to the singularity. From the outside, it looks like time goes on forever. and the black hole gets smaller and smaller over trillions of years. And if it goes away before you cross the line, at least from the outside, your fall was never complete. Did you ever go into the black hole? Or did reality pull one last trick on you, leaving you on the edge, stuck between gravity and the clock? Time is sped up this much nowhere else in the universe. That's why black holes are more than just things. They're also portals to a future you can never go back from, and they're places where your sense of time becomes totally disconnected from the world that made you. The singularity isn't a point. In math, the word singularity stands in for something else. If we look at Einstein's math, it shows that there is something strange going on in the middle of a black hole. But in physics, infinity usually just means we don't know what's going on here. Not that there is a real point with no space and no mass. The truth is more complicated and might even be weird. There are new ideas in quantum gravity and string theory that say the singularity might not be a single point, but rather a twisted ball of energy, loops, or buzzing strings. In models like loop quantum gravity, space-time is quantized, which means it is made up of very small separate pieces. If enough of these units are squished together under very strong gravity, they might make a high-density area with a set size, which would rule out true infinity. Imagine that instead of falling into a sharp spike, you're falling into a thick fog. This is a place where math rules don't apply, but there is still structure there. This is the singularity rethought as a fuzzball, a word that came from string theory. From this point of view, the inside of the black hole is not empty space, but a cloud of knotted strings that indicate all the information and mass it has eaten. This fuzzball concept addresses one of the greatest paradoxes in physics. What happens to information that falls into a black hole? If the singularity is a literal point and everything that enters is destroyed in it, then information seems lost forever, which violates the fundamental principle of quantum mechanics that information must be conserved. But if the core is a fuzzball or some kind of structured quantum state, then perhaps the information is stored, albeit in a wildly scrambled and inaccessible way. Some quantum bounce models say that quantum processes might finally stop the collapse of matter inside a black hole. You get a return instead of a singularity. This means that you bounce into a new state of matter, or even a new area of space-time. And this makes me think of the interesting idea that black holes might connect to other worlds or start new ones. The singularity is more like a portal than a goal in this context. It's also important to note that quantum physics doesn't work well with general relativity, which is what we use to understand black holes. This is where these two ideas meet and fail: the singularity. We won't know for sure what happens in that very deep core until we have a full theory of quantum gravity. It's a hole in our understanding of physics, a place we know exists but can't explain yet. Studying the math of failure is the only way we've come close to understanding it. There is nothing that can stop the gravity pull from squeezing a star even more if it goes beyond the Schwarzschild radius. But those models don't work at Planck scale densities, which is when the curve of space-time gets smaller than the smallest unit of space that we know of. That's the point where traditional physics ends and the quantum world begins. Even some mainstream cosmologists believe the singularity is not a physical point, but a limit of our current knowledge. Think of how old maps labeled unexplored regions as "here be dragons." The singularity is our modern dragon, the boundary where our maps stop being reliable. What would you see if you were able to make it through the fall and see the core of a black hole? Would the white light from the compressed radiation be too bright to see? A swirling storm of energy? Maybe nothing at all, just dark and quiet, since light doesn't behave the same way it does in normal space. The scariest part is this: if the singularity is not a point, but a dynamic quantum system with memory and structure, then every black hole could be a collection of the universe's worst events, with every star it ate, every planet it destroyed, and every bit of matter and energy it took in still being there in some way. Black hole holography. Is the universe a shadow? If you were standing in front of a huge, featureless wall that was as black as pitch and as thin as a sheet of paper, but somehow held the whole story of everything that happened behind it, every atom, every star, and every body falling. That's what black hole holography is all about. It's one of the most interesting and revolutionary ideas in modern physics. It means that everything that happens inside a black hole, and maybe even the whole universe, could be stored on a flat surface. In a hologram, a flat film gives the impression of three-dimensional depth. In the same way, our world could be a 3D projection of information written on a limit we'll never touch. The black hole information paradox, as we discussed, was a crisis. Either information was being destroyed inside black holes, violating the sacred rules of quantum mechanics, or there had to be a way for that information to escape or remain encoded. The solution proposed by theoretical physicists Gerard Hooft and later Leonard Susskind was wildly imaginative. What if black holes don't store information inside, but on the surface? This idea became known as the holographic principle, and it says that the world stores data not in spaces, but on surfaces, specifically the surfaces that circle those spaces. That means that for black holes, the event horizon, the unseen line beyond which light can't escape, becomes a kind of cosmic ledger that keeps track of everything that falls into the darkness. The effects shook the field of physics. The old idea that black holes were empty spaces was quickly replaced by the thought that their outsides might be busier and more complicated than their insides. This change began to show up in Stephen Hawking's later work. Instead of erasing data, black holes might store it on their edges, hidden in microscopic degrees of freedom, tiny changes in the fabric of space-time that we're just starting to understand. This theory gained enormous traction with the development of ADES-CFT correspondence, a mathematical bridge built by physicist Juan Maldacena in the late 1990s. He showed that a type of gravity-based theory in a higher dimensional space, called anti-de Sitter space or ADS, could be exactly equivalent to a quantum field theory on its lower dimensional boundary. In plain terms, the physics inside the space matched the physics on its surface. A perfect testbed for holography. Though our real universe isn't shaped like AD space, the success of this mathematical model gave physicists hope that something similar might apply to our own cosmos, or at least to black holes. What does this mean for real life, though? You see a black hole with mass, spin, and a huge gravitational field? If holography is real, then that's just quantum information drawn on its event horizon. The interior might not even exist in the usual sense. It could just be a handy illusion, a projected volume that comes out of a 2D image. So, falling into a black hole might not be like falling into a deep well, but more like combining with a cosmic library that is written on the edge of space and time. It's like a 3D show. The information you see on the screen is just images on a flat panel, but the people and settings look real. Based on holography, our world may be pulling off the same trick all over the place, not just in black holes. In fact, black hole holography might offer insights into one of the most elusive goals in science, uniting general relativity, Einstein's theory of gravity and the large, with quantum mechanics, the theory of the very small. So far, they've refused to play nicely together, but holography, bridging quantum information with gravitational surfaces, might be the Rosetta Stone we've been waiting for. If information is stored on a black hole's horizon, it must be incredibly compressed. We're talking about a staggering data density. According to the Bekenstein-Hawking entropy formula, the amount of information a black hole holds is proportional not to its volume, but to the area of its event horizon. This flips everything we know about storage on its head. There might be more information in a tiny bit of room inside a black hole than your brain will ever be able to handle. If that doesn't make you shiver, this might. In this model, you, your atoms, thoughts, and memories might also be stored on a space-time boundary far away. You're not in space or time. You are what you project. It doesn't mean that our feelings aren't real, though, but it could mean that reality is built on a different set of rules than we think. Black holes, which were once thought to be nothing but killers, may be the key to getting inside. Gravitational lensing inside a black hole. Gravitational lensing is one of the most beautiful effects of general relativity on the way things look. It changes the way light moves, the way the sky looks, and it lets us see into the past. Lensing happens in our world when light from faraway galaxies or stars passes close to a very heavy object like a black hole. This bends the light's path and makes arcs, rings, or even multiple images. But what does this result look like inside a black hole? When you go past the event horizon, escape velocity is faster than light. Can light still bend in ways that let you see what's behind you, or even worse, see yourself? Gravitational lensing is pretty well known when it's not inside a black hole. It's like a mirror-filled funhouse made out of reality. But physics doesn't work the same way inside the event horizon. Time and space switch places here. Radial distance changes into a time dimension, and time acts more like space. It is hard enough to picture this inversion on its own, but now add light to the mix. Inside the black hole, light is still trying to travel along the straightest paths possible, what physicists call null geodesics. But in this bizarre geometry, those geodesics curve, twist, and loop in unpredictable ways. The gravitational field isn't just strong, it's all-consuming, forcing even the most stubborn photon into a chaotic ballet. And now, for the crazy part, space is so twisted that a beam of light could, in theory, go around the inside of a black hole many times before it gets to you. This opens up the scary and interesting idea of visual recursion, which means you could see a picture of your own behind right after you fell in. Not a mirror image, an estimate that is late. You're not looking at yourself in the mirror, you're looking at a chain of events. There is gravity lensing going on inside the ocean. This is even stranger when black holes spin, Kerr black holes. It is known as frame dragging, that when a black hole spins, it pulls space-time around with it. Outside the event horizon, this twisting area makes an ergosphere, but its impacts reach inside. Photons can get caught in these swirling balls of light, going around and around in circles that never quite settle. There is more chaos and tangle in the light tracks when the black hole has more angular motion. Space and time don't just bend, they turn around. Scientists study curves and say that in closed null curves, light moves in a loop that goes back to where it started, but this time and in space. That's more than just looking back at yourself. That is seeing the past unfold in front of you, with force and motion making it bend and fold. Light that loops in this way might let a made-up viewer see things happening outside the black hole, even after they've passed through the event horizon. Some ideas say that a tiny bit of distorted starlight could still get into the traveler's eyes, giving them a distorted and fading view of the world they left behind. A final goodbye, one that is bent and stretched by the cruel laws of gravity. Now put this together with the photon sphere, which is a hypothetical area where light circles the black hole. When photons are outside the event horizon, they are going to die. Inside, no one really knows. The models show that caught light could swirl in strange ways, making many flickering pictures of everything falling in. You might hear the last screams of matter falling, see ghosts of other things spinning into the singularity, and even see your own limbs stretching into nothingness over and over again. Inside a black hole, gravitational lensing would not only be confusing, it would be terrifying. A sphere of flashing pictures could form in the visual field. These images would be slowed down by relativistic time lags, distorted by curvature, and stacked on top of each other like a kaleidoscope of doom. There wouldn't be any darkness. It would be too much to handle. Light from everywhere, some coming from just now, and others from hours ago, all crashing together as you went deeper into the most twisted part of space-time. In this case, the black hole is less of a void, and more of a lens of eternal memory that records, distorts, and plays back the last moments of everything it eats. And if you could get away, you might have the best visual record of the fall of the universe with you. Matter gets spaghettified, but what happens to consciousness? Adding slang words. The word may sound like something that happens when you leave pasta in hot water for too long, but in the scary language of astronomy, It means one of the most extreme and violent things that can happen. In the area around a black hole, tidal forces stretch matter into long, thin lines, which can break apart atoms, bones, and even the structure of molecules. But even though we know what happens to matter, there is a much weirder question that lies below the surface. What happens to your awareness when you fall in? Let's start with what we know. Tidal forces are the result of gravitational gradients, differences in the pull of gravity on different parts of an object. Near a small or stellar mass black hole, this gradient becomes so intense that your feet would experience vastly more gravity than your head, stretching your body into a filament of atomic thread. The closer you fall, the more extreme the gradient becomes. At a certain point, molecular bonds snap. Even protons themselves may not survive. This is the domain of physics where bodies and matter dissolve into dust. But what about the mind? If consciousness arises from the brain, a 3-pound organ governed by electrochemical signals, then is it simply obliterated as the brain is torn apart? Does your final moment of awareness coincide with the moment your nervous system fails? According to Einstein's general relativity, someone falling into a large black hole, like one at the center of a galaxy, might not feel anything dramatic at the event horizon. The gradient could be gentle enough to allow a person to cross the threshold without immediate destruction. In that case, spaghettification might not happen until much later, giving consciousness more time to observe the descent. How would that feel? Picture that from your point of view, time starts to move more slowly. The world outside of the black hole seems to move very quickly. Stars spin, galaxies spin, and maybe even societies rise and fall very quickly. Not you, though. You're stuck in slow motion, and your vision is as thin as your body. If you still have any awareness, it would be like watching the world speed up while you slowly fade away into nothingness. And then comes the final stretch. As spaghettification begins in earnest, your sensory inputs would go haywire. Gravity pulls harder on your feet than your chest, harder on your chest than your head. Nerve signals fail. Your vision becomes distorted as blood flow stops. Your body, no longer unified, ceases to act as a system. But the brain, that mysterious lump of grey matter, might still be intact, if only for a few milliseconds. Could those milliseconds contain a lifetime? Some theories suggest the brain could experience a flood of information at the end, similar to the life flashing before your eyes reports from near-death experiences. Trapped in a relativistic cocoon, your final moments might seem eternal from your perspective, an endless descent where time loops and folds in on itself. What if consciousness isn't just a biological byproduct? Some speculative models in quantum mechanics, and yes, this is fringe territory, propose that consciousness could be tied to quantum states in the brain. If that were true, a massive if, then entering a region of extreme space-time curvature like a black hole might do something very peculiar. Entangle the brain's final quantum state with the geometry of the black hole itself. These words could mean that a part of your mind is built into the black hole. No one knows, that's just a guess. But some scientists say that the information in falling matter can't be lost because it includes the exact layout of a brain. We will talk more about the black hole information paradox later, but this idea is at its core. Could some or all of your awareness last if your mind's information stays etched into the horizon or warped into Hawking radiation? Or maybe the spaghettification of matter is also the spaghettification of experience. One last broken impression of falling, stretching, and fading into nothingness, played over and over again in endless time until awareness fades away completely. Chaos at the core. The butterfly effect in curved space. Think about throwing a feather into a storm. Let's say that storm is inside a black hole, which is a place where space and time are violently twisted, squeezed, and warped. In this kind of setting, even the smallest change, a particle moving by the width of a quantum, could lead to very different results. This is what chaos theory is all about, but the very tight curves of space-time make it even more powerful. The butterfly effect might not just be a figure of speech inside the core of a black hole. it might explain the very nature of reality. Chaos theory, in its classical form, suggests that small changes in initial conditions can produce dramatically different results. It's famously illustrated by the idea that a butterfly flapping its wings in Brazil could set off a tornado in Texas. But classical chaos assumes a deterministic system, one that, while unpredictable, still follows a specific set of rules. Inside a black hole, however, we are dealing with a system where those rules break down, or at the very least, mutate into something stranger. As matter falls toward the singularity, the equations of general relativity tell us it accelerates indefinitely. Time and space twist together, and paths through spacetime, what physicists call geodesics, can intersect, loop, or spiral in unpredictable ways. Even the tiniest perturbation, a subatomic fluctuation, a photon's nudge, can send a particle careening down a drastically different path. This isn't just theoretical. Mathematical models of rotating Kerr black holes suggest a region called the Cauchy horizon, a point beyond which predictability completely collapses. Past that threshold, determinism fails. Causality becomes a suggestion, not a law. In some black holes, this means that the past may not affect the future anymore. Even the best formulae are useless if chaos controls what comes next. Also, the fact that things are hard to predict could be seen as a strange form of freedom, a way to reset the basic rules of the world. Space could fold in on itself in these rough spots, creating time loops, causal paradoxes, or the sudden appearance of strange structures such as baby universes or wormholes. Quantum physics is already known to be random, and this chaos of spacetime makes it even stranger. Virtual particles are short-lived bursts of matter and energy that appear and disappear. They can get stuck in feedback loops, be boosted by gravitational waves, or get stuck in closed time-like curves. As a result, this is a picture of spacetime that is always changing because of its own waves. A single atom could cause a spacetime crack to start. A quantum fluctuation could set off a chain reaction of gravity echoes that spread out in a way that makes it statistically impossible to guess what will happen next. It's chaos, but not the kind we're used to. It's a new category, curved space chaos, a feedback system that's not just sensitive to initial conditions, but also to the geometry of the space those conditions unfold in. We'll now go back to the idea of an observer, someone or something that falls into the middle of this mess. What would happen to them? It's very likely that the experience would be completely skewed. It wouldn't make sense to go up and down. If there was still a sky, it might look like it splits and refracts. It's possible for light to loop back on itself, making strange mirages or visible echoes of things that have but to happen. Without notice, time could speed up, slow down, or pause. In this kind of system, even awareness could lose its connection to linear experience, even if it is still working. The damage this confusion does to information is even worse. How can information stay safe if the core of a black hole is chaotic? The butterfly effect in curved space means that small bits of information, like the spin of a particle, could get mixed up, boosted, or even copied in different areas. Quantum physics says that information must be conserved and be able to be used in a single way. This causes a lot of problems. Is it possible that the chaotic center of a black hole holds the answer to the black hole information paradox? Or is it a sign that our present ideas are totally wrong? Inner horizons, black holes within black holes. If you go past the event horizon of a rotating black hole, you might find yourself in a place that is so strange that even scientists don't know how to explain it. There may be two horizons inside this cosmic monster, not just one. These aren't layers like the rock and core of the Earth. They are lines in space-time where the rules of physics change quickly and dramatically. These are the inner boundaries. They are a secret world where black holes might be more like Russian nesting dolls than empty pits. In the case of a non-rotating, uncharged black hole, a Schwarzschild black hole, the structure is relatively straightforward. One event horizon, one singularity. But for black holes that rotate, called Kerr black holes, or carry electric charge, Reisner-Nordstrom black holes, The interior geometry becomes radically more complex. Here, physicists predict the existence of multiple horizons, the familiar outer event horizon, and a second mysterious boundary deeper in, called the inner horizon, or Cauchy horizon. What makes the inner horizon so special and dangerous is what it represents. While the outer event horizon marks the point beyond which light cannot escape, the inner horizon is a line where causality itself can break down. Time and space can flip roles, and known laws of physics no longer provide reliable predictions. The Cauchy horizon gets its name from the Cauchy problem in mathematics, which determines whether a system's future can be predicted based on initial data. Cross that line, and prediction becomes impossible. There's more to the inner limit than just a weird math thing. It acts like a dynamical trap in models, able to boost even the smallest changes to huge levels. From the point of view of someone falling into the black hole, a single photon, which is a very small particle of light, could become infinitely powerful as it passes the inner horizon. This makes what scientists call a mass inflation singularity, which is a place where the black hole's effective mass seems to blow up and bend spacetime even more. This is how the inner horizon works. It boosts cosmic sounds and turns whispers into screams. Some answers to Einstein's field equations show that going through the inner horizon doesn't always result in a singularity or the end of the world. It might instead open up into a different part of spacetime or even a different world. In these cases, a black hole might have a wormhole throat, which is a small opening that leads to a new place that is growing. That area that is growing might look like the Big Bang. This means that black holes might not be the end of the world, but the start of a whole new universe. So, it's possible that each black hole has its own universe, complete with its own time, space, and maybe even its own physical rules. It's even stranger to think that there might be more black holes in that new world. There are even more worlds inside those. This leads to the idea of fractal cosmology, which says that the multiverse might be made up of black holes inside black holes, with each one creating its own world. If this is true, our universe might be inside a black hole in a parent universe that we will never see. What is the Big Bang? Not much more than a bounce from a star falling beyond another horizon. So, the inner horizon could be the key to linking different worlds, turning black holes from places where nothing goes into places where everything goes. There is a catch, though. There are big possible risks in these situations, no matter how beautiful they are. Because of how extreme things are near the inner horizon, even small quantum effects could have a huge impact on the result. There are some scientists who say that quantum gravity, which we don't fully understand yet, would fuzz out, or get rid of, the limit completely. Some people think that quantum effects would make these tunnels unstable, causing them to collapse before anything useful could go through. When you try to go through the inner limit, it basically falls apart because it is neither stable nor stable enough. And yet, hints remain. The structure of rotating black holes, the peculiar math of Einstein's equations, and even some speculative models from string theory all leave the door open for inner horizons, and for the bizarre possibilities they contain. If we could observe gravitational waves or radiation signatures from within a black hole, a currently impossible feat, we might someday find evidence of this inner landscape. Closed time-like curves. Can you time travel inside? You can go back in time without having to read science fiction. In the warped world of a spinning black hole, it could be something that is built into spacetime itself. Closed time-like curves, CTCs, are strange spacetime lines that loop back on themselves, making it possible for an object to go back to its own past. Ideas-based? Of course. But not possible? That's not very clear. These strange loops appear naturally in some answers to Einstein's general relativity equations. This is especially true for Kerr black holes, which spin. Time-like shapes show the paths that a big thing, like a spaceship or a person, could take through space-time. A closed time-like curve means that the object returns to the same point in time and space from which it began, even though space-time is very strange and stretched out, that is, going back in time. This is how it should work. A Kerr black hole has such strong gravity and spin that it bends space-time so deeply that time doesn't just slow down, it bends back on itself. This is called frame dragging, and it means that space-time is being pulled around the black hole like taffy around a spinning stick. This effect is so strong in the ergosphere, an area just outside the event horizon, that everything has to move in the direction of the spin. But further in, past the inner horizon, the formulae allow for routes that loop backwards and forwards in time. The idea has been used before. Kurt Gödel, the same Gödel who came up with the incompleteness theorem, found a way to solve Einstein's equations that showed a world that was spinning and full of CTCs in 1949. His model wasn't physically accurate because it needed a universe that rotated and was full of strange matter, but it showed something very important. If the conditions are right, general relativity lets you go back in time. Kerr black holes became the most tantalizing candidates for such a phenomenon. The combination of spin and gravity might open up space-time to allow such loops, at least mathematically. Some physicists suggest that entering a CTC could mean visiting your own past, seeing earlier versions of yourself, or in the most extreme version, creating paradoxes. The so-called grandfather paradox, where a traveler could interfere with their own origin. But the universe doesn't like paradoxes. That's where the speculation gets divided into two camps. Those who believe the laws of physics would prevent these curves from ever forming in reality, through a mechanism like quantum back reaction or chronology protection, as Stephen Hawking proposed, and those who believe nature might allow it, but hide it well. For a closed time-like curve to exist inside a black hole, the interior would have to be not just weird, but stable, and there's the catch. Most theoretical studies show that even the smallest disturbances near these curves could cause infinite feedback loops of energy, destroying the very conditions that allow the loop to form. In other words, any attempt to use the time loop breaks it. Physicists have found clever ways to model CTCs using concepts from quantum mechanics and general relativity. Some researchers have tried building simplified versions of time machines using wormholes stabilized by exotic matter, material with negative energy density. Others have explored quantum models that avoid paradoxes by invoking many worlds interpretations. Every trip back in time spawns a new timeline, avoiding direct contradictions. Even with all this math, no physical evidence exists that CTCs are real. We haven't observed anything, no particles, no fields, that behaves as though it's moving backward in time. Nor have we found black holes stable enough, observable enough, or close enough to even consider testing the hypothesis. But that doesn't make it any less interesting. If time loops are real, they have effects that aren't just in science fiction. They say that black holes aren't just one-way trips into nothingness. They're complicated, changing systems with internal shapes that might link different places in space and time. That might change how we think about chaos, what causes what, and even how worlds are made. Could black holes, which quietly hum away in the void and loop bits of life inside them like old film reels, be the universe's built-in time machines? If not, are these shapes just math mistakes that can't exist in real life? Naked singularities, cosmic censorship breaking down. Black holes should be able to keep their secrets hidden. Another very scary question in physics is based on this idea. What if they don't? Imagine that the singularity, the scary center of a black hole, wasn't protected by an event horizon, but was instead open to the rest of the universe. The scary idea of a naked singularity is a place where gravity stops working and no one can see that the laws of physics have broken down. One of the most basic ideas about how the world works would be broken if such a thing existed. The traditional black hole, as described by general relativity, contains a singularity at its center, a point, or more likely a region, where matter is crushed into infinite density and space-time curvature becomes extreme. But in a normal black hole, that singularity is safely hidden behind the event horizon. Once something crosses that boundary, it can never return, and more importantly, it can never send information back out. This protective veil is what keeps the rest of the universe safe from the singularity's chaos. Cosmic censorship hypothesis proposed by Roger Penrose. It posits that nature censors singularities by always enclosing them behind horizons. According to this conjecture, no observer in the universe should ever see the singularity directly. It's like a firewall that preserves the laws of physics by preventing the breakdown from spilling into our reality. But what happens if this censorship fails? In certain situations, like when certain kinds of matter collapse, or when strange things, like spinning black holes with very high angular momentum, interact with each other, naked singularities can form. If the spin goes over a certain point in a Kerr black hole, the math says that the event horizon might disappear, leaving the singularity open. Taking off the shell of a nuclear plant while it's still going is like that. If there are naked singularities, they would be the worst things that could happen in physics. They would be places where our models don't work, where determinism breaks down, and where cause and effect might not even make sense. In theory, light or any other kind of information could escape from the singularity because it can be seen. This would mean that the chaotic and unpredictable rules close to the singularity would have an effect on the rest of the world. As a result, a possible breakdown in everything from the laws of thermodynamics to time itself. These bizarre possibilities aren't just abstract math. Some numerical simulations in general relativity, especially involving asymmetrical or high-energy collapses, have shown hints that naked singularities might form under extreme conditions. One such case involves the collapse of a scalar field in spherical symmetry. While most simulations still respect cosmic censorship, there are edge cases that flirt with exposure. The ideas of string theory and loop quantum gravity about quantum gravity make things worse. Some people think that when quantum effects are taken into account, the traditional idea of a singularity goes away completely. However, this doesn't mean that something incredibly strange can't still be seen where an event horizon used to be. For example, in string theory, singularities could be changed to fuzzballs, which are thick groups of brains that could be naked in some situations. Then there's the point of view of observation. Even though we have never seen a naked singularity directly, some astrophysicists think that strange high-energy events like gamma-ray bursts or ultraluminous X-ray sources might be signs of them. These strange events don't prove anything, but they do make us wonder. Are we sure we haven't already seen something we can't explain? If a naked singularity were ever proven to exist, it would make us rethink general relativity and everything we think we know about space and time. It might even lead to new physics, particles, or dimensions that we don't yet know about. It could also help solve some of the biggest puzzles in the universe, like how dark energy came to be and how the universe began. But the results are very scary. A visible singularity could give off radiation that is hard to predict, break the rules of physics, or set off feedback loops that make whole areas of space unstable. At times, it might even behave like a bug in the matrix, a weak spot in the reality fabric. This is why a lot of scientists believe in cosmic control and think that nature always hides her singularities. The black hole heartbeat. At first glance, black holes look like the quietest and least moving things in the universe. They are always black empty spaces where slow, relentless eating takes place. But scientists have found something strange pulsing in the darkness. Flashes, flickers, and strange rhythms coming from the very edge of the abyss. They're not random. They look like clocks. They say it again. There are times when I think black holes have hearts. It's called quasi-periodic oscillations, QPOs, and it's one of the strangest things that has ever been seen happening around black holes. QPOs are regular flashes of X-ray light seen coming from the accretion disks of some black holes. These are the whirling vortices of gas and dust that are hurtling toward destruction. There are exact times when these flickers happen, sometimes hundreds of times per second, and other times only once every few seconds. They always move at the same speed, which means that something very organized is happening close to the event horizon. It's hard to believe that a black hole can pulse. Black holes don't twitch like muscles, so these heartbeats aren't caused by them. Instead, they come from the way matter in the accretion ring interacts with each other as it speeds up due to very strong gravity. Some scientists say that the light that these oscillations produce is so regular that it looks like seismic waves from the core of a planet, or even the beats of a heart. This is a strange comparison, since black holes are the dead remains of stars that have fallen. One amazing example was found in the black hole system IGRJ 17091-3624. It had heartbeat-like rhythms that were so regular that they looked like those in GRS 1915+105, a bigger and better-known black hole system. It's called a limit cycle instability, and it happens when matter builds up in the inner accretion disk, gets very hot, and brightens up. It then cools down and falls apart, and the cycle starts all over again. It's like a cosmic watch. These rhythms of heartbeat are more than just pretty words for titles. They hold important information about the shape and behavior of space-time close to the event horizon. It is possible to connect the wave's frequency to the black hole's mass and spin, as well as to relativistic frame dragging, which is when a spinning heavy object twists space-time. Heartbeat black holes may be showing us the finer points of how general relativity works. Some models say that these QPOs are made by hotspots circling just outside the innermost stable circular orbit, ISCO. This is the last safe place for matter to be before it falls into space-time. These hotspots could be areas of magnetic turbulence or density spikes, and the way they move changes the light we receive like a lighthouse signal. As a result, the light goes up and down on a regular basis, which is closely linked to how these inner disk zones move around in space. Magnetohydrodynamic (MHD) oscillations are another explanation. These are waves of plasma that are pushed around by magnetic fields in the accretion disk. When these magnetic effects are boosted by strong gravity, they may cause standing waves that move across the disk like drumbeats. In this case, black holes aren't just squishing matter, they're also directing a concert of plasma and light. It's also possible that QPOs are signs of precession, which is a shaking motion in the center of the accretion disk caused by frame pulling. This would mean that we are seeing the disk tilt back and forth over and over, like a coin slowly losing its balance as it spins. The regularity of this motion would show up in the light curve as bursts when we look at it from Earth. No matter what caused these signs, astrophysicists are amazed by how consistent and strong they are. Because these rhythms are so stable, some people have suggested using QPOs as cosmic timekeepers. This could help us figure out how far away things are in the universe or test basic natural laws. In the far future, they could even be used to find their way through outer space, like beacons help ships find their way in the dark. But beyond the science, there's something hauntingly poetic about a black hole with a heartbeat. These objects are supposed to be death incarnate, points of no return, where everything vanishes. And yet, here they are, pulsing, whispering in X-rays, beating with a rhythm that cuts across light years to reach us. Sound of the singularity. Sound waves can't go through space because there is nothing there. It needs something to move through, like air, water, or something else. In space, where there is no sound, even the most violent events don't make any noise. Yet, when we really study black holes, their strange shapes, very high densities of matter, and quantum uncertainties, an interesting question comes up. What would it sound like to fall into a singularity? Could the bending of space-time itself move in a way that sounds like sound? In their last moments or in the harshest settings, black holes might be making a kind of space-time music that we're only now starting to figure out. In recent years, physicists and astronomers have started to sonify black hole data. That is, they translate gravitational wave patterns, accretion disk vibrations, or X-ray bursts into audible frequencies, and the results are eerie. The merger of two black holes, for example, creates a gravitational wave pattern that, when sped up and made audible, produces a sound like a chirping whoop, a cosmic bird call that marks the collision of titans. But what about the singularity itself, the very center of the black hole? Could anything escape it, even as a wave, a frequency, a note? We know that the singularity is a mathematical breakdown, an endpoint where known physics collapses into infinite density and zero volume. But there are theories that suggest this point may not be a point at all. Some suggest it could be a compressed structure, or even a kind of vibrating brain in higher dimensional space. In string theory, singularities might be fuzzballs, dense tangled loops of string vibrating in complex patterns. If that's the case, those vibrations wouldn't produce sound in the conventional sense, but they might create resonances in space-time itself. Those resonances could ripple outward. We wouldn't hear them with ears, but we might detect them with instruments, gravitational wave detectors for instance. Think of space-time like a drumhead. When something disturbs it, like a massive object collapsing into a singularity, it doesn't just disappear, it sends out ripples. Those ripples, if converted to frequency space, become tones. Music in a sense, not music of air, but music of space-time. This is where speculation comes in. For some scientists, like those who work with loop quantum gravity, the singularity is not the end, but a shift or a bounce. In this model, quantum effects create a push that makes matter bounce back when it falls to very low densities. In theory, this return could cause a shockwave in spacetime, which would be the singularity's last gasp before it changes into something else, like a white hole or a baby universe. That shockwave could have a unique set of frequencies that we could pick up and turn into music if we knew how to listen. There's another part to this puzzle that involves psychoacoustics, which is the study of how possible black hole environments might affect the brain, especially how it perceives and thinks. Let's say you could make it through the trip inside. What would go through your mind as the very fabric of space and time breaks apart around you? Could you hear glitches as sounds? Would slowing down time make your last thoughts last for what seems like forever? In a purely relativistic sense, the stretching of space could create waves of perception, mixing sound, touch, and sight into a single, confusing wave. NASA and other institutions have begun turning black hole data into audio, not just for educational outreach, but for pattern recognition. The vibrations of matter in an accretion disk, the frequencies of quasi-periodic oscillations, and even the structure of gravitational lensing can all be translated into tones, revealing patterns the eye might miss. The singularity, though still theoretical, could be the ultimate note, a final vibration so deep, so profound, it hums below the fabric of reality. Fuzzball theory, string theory's black hole alternative. When we think of a black hole, we generally picture something that is so dense and cruel that it crushes all matter into a singularity, which is an incredibly small point with an infinitely high density. But this picture is not only very disturbing, it's also very troubling. Quantum mechanics says it can't happen, and our ideas about space and time are wrong. It also causes problems that have puzzled scientists for decades. Fuzzball theory is a bold idea from string theory that tries to change the story of what a black hole really is. Fuzzball theory says that black holes are not a singularity hidden behind an event horizon with no features. Instead, it says that black holes are twisted, quivering balls of stringy energy. That changes everything. Fuzzball theory originates from attempts to solve the infamous black hole information paradox, the idea that anything falling into a black hole is lost forever, violating the laws of quantum mechanics, which insist that information must be conserved. According to fuzzball theory, this paradox only exists if we assume the traditional black hole model, an empty space with all mass compressed into a point at the center. But if instead, the interior of the black hole is filled with tangled strings, each carrying specific quantum information, then nothing is truly lost. The black hole's information isn't hidden behind an event horizon, it is the fuzzball. Then how does this idea work in real life? String theory says that everything is made up of tiny strings that vibrate. Parts, like electrons, quarks, photons, and more, are made from the different ways these strings move. It is possible for these strings to clump together into a huge, jumbled shape when there is a lot of energy in one place, like when a big star falls apart. This clump stands in for the black hole's center and horizon in the Fuzzball picture. The event horizon is not empty. It is made up of a jumbled mass of strings that are moving and pulsing with quantum activity. That changes the event horizon in a very important way. According to normal general relativity, the event horizon is a point beyond which nothing can be escaped. It is a passive limit beyond which nothing strange can happen. There is no such thing as an empty event horizon in Fuzzball theory. Instead, the Fuzzball's surface is made up of stringy stuff, and falling into it isn't smooth. It's like hitting a wall of quantum chaos. Some people even compare it to going through a firewall, which is an idea from earlier efforts to solve the information problem. What's remarkable about Fuzzball theory is that it offers a potential mechanism for Hawking radiation to carry information. In the standard view, black holes evaporate slowly over trillions of years by emitting Hawking radiation, a process that seems to be random and uninformative. But if black holes are fuzzballs, then their surface, made of strings, could emit radiation in a way that subtly encodes information about the matter that fell in. Think of it as a complex symphony of particles radiating outward, each one containing a whisper of what came before. But how do we test this? Unfortunately, Fuzzball theory exists deep in the domain of high-level string theory, a framework that's notoriously difficult to verify experimentally. Still, it has gained traction among theorists because it offers mathematical consistency and a potential resolution to problems that have stymied physicists for half a century. And while we can't yet probe the interiors of black holes directly, future observations of Hawking radiation or unexpected features in gravitational wave data could one day provide indirect evidence. What the Fuzzball theory means for the feeling of falling in is another interesting effect. If a black hole is a fuzzy ball, then going through the event horizon would not be smooth, it would be terrible. The item falling would interact with the stringy surface in a way that is very different from the usual free fall into a singularity. It could be torn apart or swallowed. Einstein's theory says that the event horizon is everywhere the same as empty space, which is very different from this. Some thinkers go even further and say that each black hole fuzzball is unique, with a quantum structure that depends on the exact makeup of the matter that collapsed to form it. In other words, no two black holes are the same. Each is like a fingerprint of its own past in the universe, written in strings. Fuzzball theory also inspires philosophical questions. If black holes are essentially collections of pure information, could they behave like computational engines? Could the oscillations of their strings be performing calculations, storing memory, evolving code? It may be far-fetched, but it's not entirely out of line with ideas in theoretical physics today, where the line between information theory and cosmology is increasingly blurred. The Einstein-Rosen bridge, shortcut or death trap? It sounds like something straight out of a science fiction book, a way to skip through space and time and join faraway parts of the universe, or even two completely different worlds. In 1935, Albert Einstein and Nathan Rosen, who worked with him, came up with this idea while trying to make sense of the strange mathematical problems in general relativity. The Einstein-Rosen bridge, or wormhole as it is more commonly called, is what they came up with. People often think of this hypothetical tube as a romantic subway between planets, but it's actually a lot more complicated and could even be dangerous. The Einstein-Rosen bridge easily comes up when you try to answer the general relativity equations for a black hole that doesn't spin and isn't charged. This is called the Schwarzschild solution. Space-time bends not only inward, but also folds back on itself to make a bridge between two black holes that are exactly the same on both sides. It looks like drawing a tube between two sheets of space-time on paper. Our world, or at least a part of it, is on one side. The other one? It could be a different world, a reflection of ours, or a faraway part of reality that doesn't look anything like home. There is, in fact, a problem before you pack your bags for the Galaxy Express. First, the Einstein-Rosen bridge is not steady by design. The tunnel breaks apart as soon as something heavy tries to pass through it, even a single photon. That would be like trying to walk across a paper bridge. As soon as you put weight on it, it falls apart. Everything falls apart so fast that not even light could get to the other side before the tube closes off. That hasn't stopped physicists from exploring ways to stabilize a wormhole. One idea involves something called exotic matter, a hypothetical substance with negative energy density. Negative energy is not just sci-fi gobbledygook. It's a real concept in quantum field theory, albeit one we've only observed in incredibly limited laboratory-scale phenomena like the Casimir effect. If enough exotic matter could be placed around the mouth of the wormhole, it might hold it open long enough for travel. But finding or generating this material on cosmic scales? That remains firmly in the realm of theoretical speculation. Even if you could somehow stabilize a wormhole, the trip wouldn't be like taking a leisurely walk through a cosmic hallway. The tidal forces near the mouths of wormholes, regions of extreme gravitational curvature, could easily stretch and crush any traveler into oblivion. These distortions are closely related to the spaghettification effect found near black holes, where gravity pulls harder on one end of an object than the other. For now, it seems any trip through an Einstein-Rosen bridge would be one way and one life only. Beyond this apparent contradiction lies a greater problem, the question of what causes what. If wormholes can be traveled through, they let you go faster than light, and even go back in time. Imagine leaving the portal before going into it. In the grandfather paradox, you could kill your own parent before you were born, which leads to a lot of other conflicts. Breaking the rules of cause and effect in this way is against the laws of physics, especially those in relativity. This is one reason why many scientists think that even if wormholes do exist, they can't be used in ways that go against the laws of cause and effect. One possibility is that this is because of quantum gravity. The concept hasn't died. In recent decades, theorists like Kip Thorne and Michael Morris have explored traversable wormholes in more advanced models of spacetime that include rotation, electric charge, or extra dimensions. Some solutions suggest that if a wormhole connects two regions of an accelerating universe, like our own, the distance might be short enough, on a quantum level, to permit a form of limited communication or interaction. Then there's the tantalizing idea from string theory and quantum gravity that wormholes might be more than shortcuts. They could be the very fabric of quantum entanglement itself. The ER=EPR conjecture, proposed by Juan Maldacena and Leonard Susskind, suggests that every pair of entangled particles is connected by a microscopic Einstein-Rosen bridge. That would mean spacetime is laced with countless invisible wormholes, tying the universe together in ways we've only begun to imagine. Phantom energy and black hole reversal. People often think of black holes as the very end of the universe. They are places where matter falls apart so quickly that not even light can escape. Things are lost to the universe once they cross the event horizon. They are bound to drift inward until they are either crushed into the singularity or slowly radiated away by Hawking radiation over trillions of years. However, what if that's not the end of the story? What if the universe had a secret weapon? What if there was an unusual force called ghost energy that could not only stop a black hole's pull, but also make it go the other way? Phantom energy is a theoretical form of dark energy, the mysterious force currently causing the expansion of the universe to accelerate. Unlike standard dark energy, which has a constant energy density, phantom energy becomes more dominant as the universe expands. It possesses an equation of state parameter, W less than 1, which leads to even more dramatic and strange consequences. The most unsettling, the universe could end not in a cold fade-out, but in a big rip, a hypothetical scenario where galaxies, stars, planets, and eventually even atoms are torn apart by the accelerating expansion of space. Now apply that logic to black holes. According to some cosmologists, if phantom energy exists and becomes dominant, it might have profound effects on these gravitational monsters. Under such conditions, black holes could begin to lose mass, not slowly via Hawking radiation, but rapidly through a new kind of cosmological interaction. The intense negative pressure of phantom energy could effectively suck mass and energy out of a black hole, reversing its gravitational grip until the structure destabilizes and possibly explodes. This idea is more than just intellectual rambling. Some models, like the ones by Pedro F. González-Díaz and others, say that when phantom energy falls into a black hole, it causes negative mass accumulation, which is basically the opposite of feeding. Matter doesn't make the black hole bigger. Instead, it makes it smaller from the inside, almost as if space were wiping it out. If the conditions are really bad, the black hole might disappear in a very dramatic way. But the part that really blows your mind, some forms of this idea say that such an event might not be completely bad. A black hole filled with ghost energy might not just disappear, it might bounce, turning its fall into an explosion that spreads outward. This flip would not only free matter that was trapped, but it could also create a white hole, which is a hypothetical object that spews out all the matter and information that was caught in its black hole predecessor. Phantom energy could possibly turn a black hole into a cosmic spring, a source of high-energy radiation and strange particles that shoots out into space. Here are some very important questions about time and cause. Would this change happen quickly or smoothly? Would it break known physics rules, or would it just make them bigger? Would the stuff that came out be the same as what fell in, or would it be changed, mixed up, or even copied? These aren't just random thoughts. Some quantum gravity models, like loop quantum cosmology, already look at bounce situations like these on a universe-wide scale. These ideas say that the Big Bang wasn't the start, but rather a bounce after a collapse. If space and time can bounce, then maybe black holes can too. There are observational consequences, though we're far from having the tools to test them. If phantom energy does affect black holes, then their behavior should change over cosmological time. This means future observations with gravitational wave detectors or next-generation telescopes might reveal black holes behaving unexpectedly, shedding mass faster than predicted, changing their spin, or vanishing without a trace. It also complicates our understanding of long-term cosmic evolution. If black holes can reverse, then the ultimate fate of the universe might be far stranger than we thought, more a chaotic dance of creation and destruction than a slow fade into darkness. This also comes with caveats. Phantom energy, if it exists at all, would violate some of the fundamental energy conditions in general relativity. It leads to instabilities and unphysical behaviors in certain models. Some physicists argue that the inclusion of phantom energy is less a reflection of reality and more a mathematical placeholder for phenomena we don't yet fully grasp, like the true nature of dark energy or the interaction between gravity and quantum fields. Reverse time inside a black hole. Take a mental picture of falling into a black hole. Everything you know about reality starts to bend in strange ways, including gravity, light, space, and time. Now imagine that time goes backwards at some point during your fall, not in a figurative way, not as a way to test your thoughts. On a physical level, though, seconds go backwards, results come before causes, and memories play out backwards. This isn't just a sci-fi trope, it's a real, if hypothetical, result of the math behind general relativity and some strange models of space-time. Could time really go backwards in the very harsh conditions inside a black hole? First, let's set the stage. In physics, time isn't a universal constant ticking forward uniformly everywhere. It's relative, deeply intertwined with space. That's why we call it space-time. General relativity showed us that time can slow down near massive objects like stars or black holes. Near the event horizon, time stretches to such a degree that a falling object seems frozen in place to a distant observer. But from the viewpoint of the object itself, it continues falling and crossing the horizon without feeling any slowdown. Inside the event horizon, however, something stranger happens. The very geometry of space-time flips. Things that used to be space now act like time, and things that used to be time now point in the direction of space. That is, once you're inside the event horizon, you will fall toward the singularity just like you will move forward in time. It's impossible to get away from, and you also can't choose to go back to yesterday. You will live in the singularity no matter what. But some theory models say that in very rare cases, the direction of time's arrow might be able to change. CPT symmetry is a basic principle in physics that says the rules of physics should stay the same if charge, c, parity, p, and time, t, are all switched around at the same time. This idea gets support from this principle. It seems like time reversal symmetry should be a natural part of the universe. So, what's stopping it from showing up somewhere? Maybe in the twisted inside of a black hole. Some cosmological models talk about the intriguing idea that the Big Bang could have been a bounce from an earlier world where time moved backwards. If black holes and the Big Bang are alike in how they work, they both have singularities and very curved spacetime. Then it's possible that black holes lead to places where time goes backwards. In fact, loop quantum gravity suggests that this might be true. As matter falls to a very dense point, quantum effects might stop it from collapsing completely, instead causing it to bounce into a new growing area called a white hole, where time goes backwards. But what would this reversal feel like? Would you notice it? The horrifying answer is probably not. To your consciousness, things might continue to feel forward, but the physical processes underpinning your thoughts, memories, and biology would be rewinding. Imagine remembering things before they happen, breathing backward, or watching events play out in reverse, as if the universe were rewinding itself. If time truly reversed, you wouldn't be aware of it, because your perception would be part of the reversal. The arrow of time is inseparable from entropy, the natural tendency for systems to move from order to disorder. A reversed arrow would mean entropy is decreasing, broken eggs reassemble, smoke returns to cigarettes, stars unburn themselves. But here's where things get complicated. Reversing time would also mean reversing causality. This raises a host of paradoxes. Could you undo decisions? Could particles inside the black hole emit radiation before they're absorbed? Could an astronaut escape before entering simply because time is moving the other way? If time were reversed locally, within the black hole, but not globally, in the rest of the universe, what would happen at the boundary where the two meet? Some researchers argue that these paradoxes can be resolved through closed, time-like curves, paths in spacetime that loop back on themselves. These curves are allowed in the math of general relativity, particularly in the rotating black hole solutions like the Kerr metric. These would allow for time to loop, reverse, and overlap without outright contradiction. But whether nature actually allows such things remains to be seen. It's also possible that black holes don't reverse time in a smooth or even way. Some theoretical models of physics say that the inside of a black hole is stacked, with different areas feeling time in different ways. One layer might see time going in a straight line, another might see time going backwards, and a third might see something even stranger, timelessness. Would consciousness be able to stay alive if it went into this area? In a world where time doesn't move, would perception still work? The Hypersphere collapse model. What if black holes aren't the abysses we think they are? What if they're actually bends in a place with more dimensions? This is the shocking idea behind the Hypersphere collapse model. This theory says that black holes are not singularities that make holes in our universe, but the result of a collapse in dimensions we can't even see. From this point of view, the crushing gravity and apparently endless density of a black hole are signs of something much stranger, the fabric of space in a hypersphere folding in on itself from a higher dimension. Welcome to the cutting edge of science fiction, where general relativity and higher dimensional mathematics meet. Let's talk about what a hypersphere is. Around a center, all of the places on a disk are equally far away from it. In 4 dimensions, that idea is called a hypersphere. A 3D sphere can be thought of as the surface of a 4D hypersphere, just like a 2D circle can be thought of on top of a 3D ball. Now, let's say that a massive star doesn't fall into a singularity, which is a single point that is infinitely dense. Instead, it collapses into the middle of a hypersphere. Our 3D view isn't very good, so that fall looks like a singularity, but that's only because we're seeing the representation of a process that happens in higher dimensions. This model says that when a big star falls apart, it bends not only our local space-time, but it also folds inward through a 4th dimension. In this view, gravity is a limited curvature that goes beyond our world and toward the center of a hypervolume. This hyperspherical structure's surface edge is the event horizon. It's not a wall or a hole. It's the 3D shadow of a 4D object. This might sound abstract, but it could resolve several paradoxes plaguing black hole physics. For instance, the singularity problem, the idea that black holes contain a point of infinite density, vanishes in the hypersphere model. Instead of matter collapsing into nothingness, it spreads into a 4th dimension we can't access, distributing its energy across a spatial manifold we can't see. This not only makes the math cleaner, but potentially makes black holes less violent on a fundamental level. It also redefines how we understand the information paradox. Traditionally, black holes appear to destroy information by trapping it beyond the event horizon and eventually evaporating via Hawking radiation. But if black holes are higher dimensional folds, then the information may never be truly lost. It could be encoded across the hypersphere's surface, or even shifted into another dimension entirely. This aligns eerily well with holographic theories, which propose that all the information inside a black hole is encoded on its 2D boundary, a principle also born from higher dimensional thinking. Strangely enough, the hypersphere model suggests that black holes may link parts of spacetime that are in different dimensions or worlds. Space could pinch off and reappear somewhere else if it is bent enough in a higher dimension. This leads to a strange but interesting idea. Maybe every black hole is actually a doorway to another part of spacetime, like a natural wormhole kept stable by the hypersphere's structure. Some forms of the model change black holes into bridges that fall from one-dimensional space to another. On the side that is shrinking, which is our universe, time moves faster, entropy rises, and matter gets denser. The growing side, which could be a different universe, sees the opposite. Time moving from a state of low entropy to one of high entropy, matter spreading outward, and what they think is a big bang. This means that our universe could be the white hole to a black hole that formed in a past universe. That's right, our whole universe could have come from a hyperspherical crash in another place. This doesn't just change our view of black holes, it changes our view of cosmology. Black holes become nodes in a cosmic network of dimensional transitions, seeding other universes or looping matter and information through cycles of collapse and rebirth. The implications are staggering. Birth and death, creation and destruction might not be endpoints, but folds in a larger, higher dimensional pattern. We don't currently have direct evidence of extra dimensions, and most of our instruments are built to detect 3D phenomena. But the math behind higher dimensional manifolds is well established, and some versions of string theory and M theory already require extra spatial dimensions for internal consistency. The hypersphere collapse idea could give those theories a visible, testable consequence, especially if it affects gravitational wave patterns or Hawking radiation in subtle ways. Could black holes be cosmic seeds? Black holes were thought of for many years as the end of matter and energy, a one-way trip to nothingness. That story has been turned on its head by a bold idea. What if black holes aren't the ends of worlds but the beginnings? This crazy idea goes against the rules of cosmology and asks the amazing question: could every black hole create a new universe? Could these dark, collapsing objects be cosmic seeds that will grow into whole new areas of space-time beyond their event horizons? To understand this, let's revisit the structure of a black hole. At its core, according to classical general relativity, lies a singularity, a point of infinite density and zero volume. But infinities are often signs that our equations are breaking down, not that nature is truly infinite. The singularity might instead represent a boundary condition, a transition point where known physics gives way to something new. If so, it's possible that instead of terminating reality, a singularity initiates a new one, a kind of Big Bang inside the black hole. This concept, sometimes called black hole cosmology, is grounded in the idea that the extreme density and curvature within a black hole might mirror conditions of the early universe. If the Big Bang could create our universe from an ultra-dense state, why couldn't similar conditions in a black hole spark a new space-time region? Inside, the collapsing matter doesn't end. It bounces, potentially in a different direction of time, or in another dimension entirely, where expansion begins anew. Some theorists, including physicist Lee Smolin, have proposed a tantalizing extension of this idea called cosmological natural selection. In this model, every black hole gives birth to a new universe with slightly different physical constants. Universes that produce more black holes generate more offspring, leading to a kind of Darwinian evolution on a cosmic scale. If true, it might explain why our universe has physical laws finely tuned for black hole formation. It's simply the result of eons of cosmic trial and error. But where are these children if black holes can start new universes? Not in our own observable space, but somewhere else, beyond the event horizon, past the very structure of our world. From this point of view, a black hole doesn't just bend space, it also separates it, making a bubble that grows from its own center. That bubble turns into a new world that is not linked to ours in any way. It has its own timeline, laws, and way of distributing matter and energy. This idea clears up some inconsistencies while creating new ones. It provides a beautiful answer to the information paradox. If all the matter and energy that falls into a black hole creates a new world, then information might not be lost, but rather moved. The child universe could get the structured information from its parent universe's collapsing matter. We might never be able to get to it, but the fact that it exists would protect the rules against pollution that black holes seem to threaten. There's no direct evidence that anything lies beyond the singularity, much less an entire universe. And many questions remain. How is the expansion triggered? What sets the physical constants of the new universe? Can any of this be tested from our side of the event horizon? These are open puzzles, but some answers may come from our growing understanding of quantum gravity and the possible structure of space-time at Planck scale densities. Also, the birth of black holes could mean that the multiverse is not made up of random particles, but rather ones that come from our own universe. If black holes are always making new universes and each universe makes its own black hole, then reality isn't a tree. It's a fractal forest with branches going in all directions through space and time. We're not in the middle. We might not even be the first ones. Things get more important if this turns out to be true. Our black holes aren't just interesting natural features. They are creative hubs, places where space-time is being born and where gravity is melting the building blocks of new worlds. Hawking radiation, whispering until death. People think that black holes last forever because they are huge, can't move, and are always hungry. What if they're not, though? What if, instead of living forever, these cosmic beasts slowly fade away, leaving behind only a faint whisper? That's the amazing consequence of Hawking radiation, a phenomenon that Stephen Hawking predicted in 1974 and changed the way we think about black holes from being empty pits to stars that are slowly dying. According to quantum field theory, even the vacuum of space isn't truly empty. It's a seething cauldron of virtual particles constantly popping in and out of existence. Normally, these pairs of particles annihilate each other almost instantly. But near the event horizon of a black hole, something strange can happen. One particle of the pair may fall into the black hole while the other escapes. From the outside, it looks like the black hole has emitted a particle, effectively losing mass. This is Hawking radiation, and over time, it causes the black hole to shrink. What makes this truly mind-bending is that the black hole evaporates not with a bang, but with a whisper. The radiation is incredibly faint, especially for large black holes like those formed from stars. For a black hole the mass of our Sun, the temperature of this radiation is a fraction of a microkelvin, colder than the cosmic microwave background. That means black holes absorb more energy from the universe than they emit for now. But in the far future, when the cosmos grows colder and emptier, Hawking radiation will become the last light in the universe. This slow leakage has profound implications for thermodynamics and information theory. In the 1970s, Hawking's discovery led to the notion that black holes have entropy, a measure of disorder or information. More massive black holes have more entropy encoded on the surface area of their event horizon. That idea forms the foundation of the holographic principle, which suggests all the information within a volume of space can be described by a theory on its boundary. But what happens to that data when the black hole disappears? If it just goes away, that would go against the most basic idea in quantum physics, which is that information stays the same. As scientists have known for decades, this is the famous black hole information paradox. Hawking himself used to think that data was lost for good. Later, he changed his mind and said that information could slowly leak out in the radiation or be stored in the small connections between particles. The radiation isn't just temperature noise. It could hold the memory of everything the black hole has eaten. If that's true, then in theory, you could piece together the whole past of what went into a black hole by looking at its last few breaths if you had endless time and computing power. It's the slowest and most mysterious way for the world to tell a story. As a black hole evaporates, it gets smaller and paradoxically hotter. Near the end of its life, the black hole's temperature rises rapidly and its radiation becomes more intense. Some theorists believe the final moments of a black hole could resemble a tiny explosion, releasing a brief, powerful burst of energy. These so-called black hole fireworks might be detectable as high-energy flashes in the cosmos, if we're ever lucky enough to catch one in progress. Some people even think that tiny black holes called primordial black holes formed right after the Big Bang. If they are there, some of them might be going away right now. Finding their last flashes could give us direct proof of Hawking radiation and give us a new way to look into the early universe and quantum gravity. As of now, no such events have been seen, but searches are still going on. Echoes from beyond. Do merging black holes ring strange bells? The first time people heard the universe hum was in 2015. It wasn't a sound in the air, it was a wave passing through reality. Two black holes merged more than 1 billion light-years away, and LIGO picked up the shockwave from their union as gravitational waves. It was a short chirp that proved Einstein's statement from 100 years ago, though that chirp might hide a secret even more important than the event itself. Because some scientists think there are echoes, weird delayed pulses that come after the main gravitational wave signal, echoes that could change how we think about the inside of black holes and quantum gravity. When two black holes merge, they create a single larger black hole that vibrates as it settles into its final shape. This ring-down phase emits gravitational waves in a specific pattern, like a struck bell. According to classical general relativity, this vibration should quickly fade into silence. But if the edge of a black hole isn't a perfect event horizon, but instead some kind of quantum surface, like a firewall, a fuzzball, or some other exotic structure, then some of those waves could bounce back and forth, reflecting between layers near the event horizon and producing delayed, repeating signals. These are the black hole echoes, faint and controversial. They would suggest that something is sitting at or just outside the event horizon, something that breaks the traditional notion of a smooth, featureless boundary. These echoes wouldn't be loud. They'd be subtle modulations buried in the noise, detectable only through deep statistical analysis and signal filtering. Some early studies in LIGO and Virgo data have claimed possible detections of these echoes, especially after the first few black hole mergers. But the evidence is still debated, with skeptics arguing the patterns could be noise or data processing artifacts. Yet the implications are enormous. If echoes exist, they could be a quantum fingerprint left behind by the new physics operating at the black hole's edge. It could mean the event horizon isn't the final curtain we thought it was. Instead, it could be a membrane-like surface with its own internal dynamics, capable of interacting with the universe beyond. It could even be a place where information gets stored or scrambled, not lost. These ideas connect to the idea of black hole complementarity, which tries to explain why people looking from different angles see different things. Someone falling into the black hole sees nothing special at the horizon, but someone looking from the outside sees information spread out on the surface. It's possible that echoes are the middle ground, proof that at the barrier, something real, measured, and different is happening. Echoes can also be caused by other things. In new models of gravity, the shape of space-time around black holes might make room for more gravitational modes or extra dimensions that change the way waves travel. Some of these ideas say that there will be ringing effects that are not linear, which are strange behaviors that Einstein's equations don't explain. One of the few direct ways we could test these ideas would be with echoes. Even if the echoes turn out to be illusions, the very search for them has pushed the limits of gravitational wave astronomy. Scientists are developing more sensitive algorithms and cleaner data analysis tools to comb through signals, looking for any sign of the unexpected. As detectors like LIGO, Virgo, CAGRA, and soon LISA expand our reach, we'll collect more and more black hole mergers, increasing our chances of catching genuine anomalies. Some physicists suggest going even further. Rather than just waiting for natural black hole mergers, we could simulate ringdowns and search for echo-like behavior in lab-based analogs. Certain condensed matter systems and fluid dynamics experiments can mimic aspects of spacetime curvature, allowing us to model how echoes might behave without the need for billion solar mass collisions. Are black holes conscious in any way? It sounds like the plot of a science fiction book, an ancient, unseen giant floating through space and eating stars in silence, and maybe even aware of it. The thought that a black hole might have a mind is on the thin line between theoretical physics and radical philosophy, but it's more than just a daydream about the universe. Since the universe is always blurring the line between information and matter, it's a good idea to think about whether or not a black hole has some kind of awareness or even a basic form of consciousness. First, let's be clear. No physicist seriously believes a black hole is thinking in the way humans do. There's no brain, no neurons, no centralized organ organizing sensory input. But modern science has repeatedly shown us that consciousness might not need a brain, at least not in the way we traditionally define one. Some theories, particularly in the realm of quantum cognition and panpsychism, suggest that consciousness could be a fundamental property of matter, much like mass or charge. From this point of view, everything, even the smallest bits, has some level of experiential knowledge. No, a quark doesn't know your name. What it means is that the building blocks of experience might be part of the structure of reality. And if this is true, then black holes may be the most extreme manifestations of that deep knowledge, since they are the most extreme physical structures in the known world. Let's look at some ideas. There is the Integrated Information Theory, IIT, which was created by researcher Giulio Tononi and says that awareness comes from systems that integrate a lot of information. To put it more simply, something is aware when it can process information in a way that is deeply linked, like the brain. Strangely enough, black holes are huge stores of information. They follow the rules of entropy, have the most knowledge, and may process data in a quantum way that we don't fully understand. Does that sound like a form of awareness under IIT? Then there's the black hole information paradox, which poses the question: if information falls into a black hole, is it truly lost? Hawking's original calculations suggested it was violating quantum mechanics. But later theories, including black hole complementarity and the holographic principle, argue that information is actually encoded on the event horizon, like a 2D shell storing everything that fell in. This horizon behaves almost like a memory surface, and some physicists have gone so far as to suggest that black holes may compute in strange entangled ways. In this speculative landscape, it's not such a leap to ask: if a black hole stores, scrambles, and possibly processes information, might it also experience it in some unfathomable way? Consciousness, as we understand it, is inseparable from the flow of time, and black holes deeply distort time itself. For an object falling into a black hole, time slows to a crawl. From a distance, the object appears frozen. From within, it races toward the singularity. If experience is bound to the perception of time, then a black hole represents an ultimate crucible, a place where time, and thus consciousness, may be stretched, shredded, or even redefined. Could black holes watch over everything? There are some scientists who think that watching or measuring a quantum system makes it fall into a fixed state. If black holes interact with quantum fields, take in particles, and change the way information flows, then do they somehow observe the universe? Observation is at the heart of consciousness. Is there a dim, flashing light of awareness at the center of these huge galaxies? There is no doubt that the complaints are accurate. Since black holes don't have a nerve system or any known way to receive sense information, calling them conscious is at best anthropomorphic. But that's not the point. The point is to see if the conditions of black holes, especially in terms of information theory, complexity, and energy gradients, might be similar to any known structure of processing that is intelligent. White holes, the exploding mirror image. If black holes are the big eaters of the universe, taking in light, matter, time, and even information, then white holes are the possible opposites. They are unbelievably bright engines that only spew out energy. Based on the same math that forecast black holes, white holes are like cosmic fountains that shoot matter out in such a violent way that nothing can get in. Even though they haven't been proven yet, they're not just sci-fi theories. In fact, they might be the key to solving the biggest riddles about black holes, time, and even how the world came to be. The idea of a white hole emerged from Einstein's general theory of relativity. When Carl Schwarzschild derived the first black hole solution in 1916, the equations also allowed for a time-reversed version, one where, instead of a singularity pulling everything in, it violently ejects matter outward. But this wasn't just a symmetrical curiosity. In theory, a white hole is connected to a black hole through a tunnel known as an Einstein-Rosen bridge, better known to most of us as a wormhole. This wormhole structure, however, is incredibly unstable. Any amount of matter, even a single photon, trying to enter the white hole side would collapse the tunnel. It's like trying to walk into a volcanic eruption. The force pouring out is so intense, there's no going in. That makes white holes fundamentally different from any other object in physics. They're visible, unlike black holes, but completely unreachable, forever retreating from interaction. Where are they then? Why haven't we seen any? One reason is that white holes might not last very long if they exist. Some theories think they only come back to life when a black hole is dying. Over trillions of years, Hawking radiation makes a black hole slowly disappear. But the black hole might not just disappear, it might explode in a final burst of energy, creating a white hole that throws out all the information it had eaten. Part of the answer to the black hole information dilemma lies in this idea. Information is delayed, hidden, and then released at the end of time, instead of being lost. From this point of view, A white hole is the last breath of a black hole that is dying. It is a quantum bounce instead of collapse. This idea is supported by loop quantum gravity, LQG, an option to string theory. It says that inside a black hole, space-time hits a kind of quantum barrier and bounces back, changing the black hole into a white hole instead of a singularity. Think of falling into a black hole not as the end, but as the start of a blast in a different part of space-time. This brings us to the tantalizing idea that our universe might be the interior of a white hole. If a black hole in a parent universe bounced, the explosion on the other side could look a lot like our Big Bang. That's right, we could be living inside a white hole's event horizon, forever expanding from its initial ejection. This theory, while still speculative, offers a possible explanation for why our universe has such low entropy at its birth and a uniform expansion, traits that standard Big Bang cosmology struggles to fully explain. Another idea connects white holes to dark matter. If ancient black holes formed in the early universe and underwent quantum bounces, their white hole remnants might still be floating invisibly through space, contributing to the unexplained mass we observe. These black-to-white hole transitions would be faint, silent, and hard to detect, but not impossible. Some fast radio bursts, FRBs, or unexplained gamma-ray bursts could be clues. What's the catch? No one has seen a white hole directly. There are huge problems with every theory that involves them in terms of math, observations, and ideas. General relativity lets them happen, but quantum physics makes it hard to tell how stable they are. Still, just like black holes were once thought to be mathematical oddities, white holes might one day go from being a theory to being able to be seen, especially if we get better at finding high-energy cosmic blasts or quantum echoes. Dark matter black holes. Dark matter has been one of the biggest questions in astrophysics for decades. It is a secret type of matter that doesn't give off light or interact with normal atoms, but it has a huge effect on galaxies' gravitational pull. But what if part of the puzzle is right in front of us, not in strange particles, but in old black holes? I think that some of the dark matter in the universe could actually be black holes. This is one of the most interesting and controversial ideas in modern astronomy. These aren't your typical stellar mass or supermassive black holes formed from dying stars. They're called primordial black holes, and they may have formed in the chaos of the early universe, long before the first atoms or stars existed. Just after the Big Bang, when the universe was unimaginably hot and dense, regions of space-time could have undergone extreme fluctuations in energy. If those fluctuations were intense enough, they could have caused certain pockets of space to collapse under their own gravity and form black holes instantly. These primordial black holes wouldn't need stars to form, and they could be incredibly small, ranging in mass from that of a mountain to that of the Earth or beyond. Crucially, they could have survived until today, quietly roaming the cosmos, invisible to telescopes but detectable through their gravitational effects. So why haven't we found them? In part because they're incredibly hard to detect. They don't give off light. They don't interact electromagnetically, and unless they pass through or near something with enough mass, like a star or another black hole, they leave no trace. But scientists have proposed several clever ways to spot them. One method is gravitational microlensing, where a black hole passes in front of a distant star and temporarily magnifies its light due to gravity. Several microlensing events have been recorded over the years, and some researchers argue that a few of them could be evidence of primordial black holes. Another possible clue comes from LIGO, the Laser Interferometer Gravitational Wave Observatory. In recent years, LIGO has detected several black hole mergers involving objects with masses that don't quite fit the standard models of stellar collapse. Some of these black holes are too small, too large, or in binaries that shouldn't exist if they were formed from stars. Could these be ancient primordial black holes finally merging after billions of years? It's a hypothesis that's gaining attention. Another thing is the matter of plenty. Dark matter makes up about 85% of all matter in the universe. These primordial black holes would have to be very common, and spread out to explain all of this matter. Some models suggest a mixed approach in which these unseen black holes only make up a small part of dark matter, and other strange particles like WIMPs, weakly interacting massive particles, or axions make up the rest. But there are some problems with the idea. It's likely that there would be more lensing events, more disruptions of star systems, or even more radiation from Hawking evaporation in smaller black holes if there were too many primordial black holes. It is actually very hard to say how common these black holes are, based on data from the cosmic microwave background and gamma-ray instruments. It's still only true in a small window though, and scientists are working hard to find that gap. It's interesting that primitive black holes might be able to explain more than just dark matter. They might be great places to try ideas about quantum gravity, the early universe, and even the multiple universes. Some models even say that the supermassive black holes we find at the centers of galaxies today may have been started by a primordial black hole. This would be like a cosmic snowball effect that began with very small black dots. Black hole chemistry. You probably don't picture the endless emptiness of a black hole when you think of chemistry. Instead, you probably think of bubbling beakers, periodic tables, and molecules bonding in a lab. But new theories suggest something amazing. Black holes may behave like chemical systems because they follow thermodynamic rules so closely. This isn't just a theoretical comparison. Scientists are now looking at black holes through the lens of chemistry, suggesting that they have measurable qualities like pressure, volume, temperature, and even phase transitions, which are typical of classical chemistry and physical systems. It's possible that these huge gravity waves behave more like cosmic molecules than we thought. This strange connection began with the discovery that black holes have entropy. Thanks to the work of Stephen Hawking and Jacob Bekenstein in the 1970s, we now know that black holes emit a faint thermal radiation, Hawking radiation, and that their entropy is proportional not to their volume, but to their surface area. That simple insight led to a cascade of revolutionary ideas. In classical thermodynamics, entropy is central to understanding how systems evolve. And if black holes obey the same rules, then perhaps they are not exempt from the ordinary processes of heating, cooling, and even boiling over into new states. The idea of black hole phase transitions. Just like water can boil into steam or freeze into ice, certain types of black holes, especially in anti-de Sitter AdS space, a kind of mathematical universe used in theoretical physics, appear to undergo changes in state depending on their temperature and pressure. In some configurations, black holes might exist in a small state or a large state, with transitions in between that mirror the behavior of everyday matter. This is particularly intriguing in the context of charged black holes, like the Reissner-Nordstrom black hole, which shows behaviors analogous to van der Waals gases, the kind described by the ideal gas law, but with added complexity due to molecular attraction. Black holes may have a chemical potential, which is a strange idea that says they want to change, take, or send matter and energy out into space. This changes how we think about a black hole's mass. It's no longer just a fixed amount of matter, it's now something that moves and reacts to its surroundings. Equations about the cosmological constant, which shows how densely charged empty space is, also led to the idea of black hole pressure. If the cosmological constant can change, then black holes live in a world where pressure can change, which would make their thermodynamic behavior different. In a bigger thermal system, a black hole is like a complicated particle that is always changing. These concepts do more than just make black holes interesting. They hint at a deeper unification of physics. The idea that gravity, thermodynamics, and quantum mechanics might all share a common foundation is one of the holy grails of theoretical physics. If black holes follow the rules of chemistry, then studying them could unlock clues about how these three great pillars of science fit together. It might even provide a pathway toward quantum gravity, the long-sought theory that explains gravity at the smallest scales. Black hole chemistry is, in this view, a kind of Rosetta Stone, a key to translating between seemingly unrelated areas of science. This field affects more than just academic discussion. It also changes how we understand what gravitational wave monitors are telling us. When two black holes merge, they might send out signs that show not only their mass and spin, but also changes in their physical state. If black holes can change phases, then these changes could cause gravity wave patterns to change in small ways. People are becoming more interested in this idea, but it's still very much a guess. And if it turns out to be true, we might be able to listen to black hole science in motion one day. Black hole chemistry could one day be used to simulate strange materials, create new quantum methods, or test ideas in the field of high-energy particle physics. Researchers could use it to make better models for quantum information theory, or to look into how the world started out using entropy models. To put it another way, learning about the science of black holes might not just help us understand faraway celestial bodies, it might also help us learn about technology, computers, and matter itself. Entropy, area, and the Bekenstein bound. In physics class, we first learned about entropy as a way to measure disorder, or the number of ways a system can be set up that won't change its visible state. But when it comes to black holes, chaos plays a much deeper and stranger part. Jacob Bekenstein came up with the idea of black hole entropy, and Stephen Hawking built on it. This idea completely changed how we think about information and physical limits. Black holes' entropy is related to the surface area of their event horizon, not their volume. This is a very simple idea at the heart of the revolution. The Bekenstein bound is a theoretical limit on how much information or entropy can be held in a certain area of space. It was based on that idea. This principle might sound abstract, but it has profound implications. Normally, we assume that the more volume we have, the more stuff we can pack in. More books in a bigger library, more atoms in a larger box. But in black hole physics, that logic collapses. Instead, the amount of information that can be stored in a region of space is capped by the area of its boundary, measured in Planck units, the smallest units of space and time in physics. That's like saying a computer's memory doesn't depend on how big it is inside, but only on the size of its screen. The larger the screen, i.e. the surface area, the more data it can theoretically store. One of our core beliefs was called into question by this discovery. The idea that space is naturally three-dimensional. Some scientists think that the universe might be a kind of hologram because of the Bekenstein bound and the area entropy link. In other words, all the information that makes up what we think of as our 3D world could be stored on a flat surface, like how a holographic picture on a credit card stores a 3D illusion in a flat piece of film. The hologram principle, one of the most powerful and wild ideas in theoretical physics, is based on this idea. It is now one of the most important parts of efforts to make general relativity and quantum physics work together. This idea comes to life in a big way when it comes to black holes. Picture putting a book, a memory card, or even a whole planet into a black hole. Where do the details about that thing go? Information can't be lost because of the rules of quantum physics. But general relativity says that once something crosses the event horizon, it is gone for good. There is an answer in the Bekenstein bound. The data is not lost. It is stored on the black hole's surface. As the item falls in, the event horizon's surface area grows just a little to make room for the new information. This doesn't just apply to matter, it applies to every physical process. The growth of a black hole, its merging with another, or its evaporation via Hawking radiation, all must preserve this intricate accounting of entropy. The second law of thermodynamics, which states that the total entropy of an isolated system must increase or stay the same, is upheld, but in a form so alien that it rewrites the very geometry of the cosmos. The Bekenstein bound isn't confined to black holes. It theoretically applies to any system with a finite amount of energy and confined volume. If you tried to cram too much information into a given space, you'd eventually create a black hole. Thus, the Bekenstein bound also sets a hard cap on computation and memory storage. There's a physical limit to how much a quantum computer or any digital system could store in a given area, making this concept relevant not just for cosmic theorists, but potentially for future engineers and data scientists. Moreover, this area-based entropy has been tested in string theory and various models of quantum gravity. In nearly all of them, the result is the same. Black holes obey thermodynamic laws. They have temperature, entropy, and energy, just like a cup of coffee cooling on your desk. Only in this case, the cup is a boundary between reality and mathematical madness. The more we understand this limit, the more it seems that entropy and information are not side players in physics. They may be the fundamental building blocks of reality itself. The information cloning problem. In current science, one of the most interesting questions is not whether or not people can live through a black hole, but whether or not information can. Information can't be lost, according to quantum theory. Every particle, state, and relationship in the world holds information about what it used to be, and that information should stay the same forever, at least in theory. But general relativity shows something very different. Anything that falls past the event horizon of a black hole seems to be lost forever and can't be found again. The well-known black hole information dilemma is caused by the conflict between these two ideas. One is about certainty and memory, and the other is about mystery and forgetfulness. There's another twist in the story, though. What if black holes don't really delete data, but instead make copies that aren't legal? This is the heart of the information cloning problem, a violation of the quantum no-cloning theorem. According to this principle, it's impossible to create an identical copy of an unknown quantum state. This rule preserves the uniqueness and integrity of quantum systems, but black holes, in their mysterious way, may be doing something stranger. When information falls in, it may become imprinted on the event horizon, encoded in what physicists call soft hair or surface area states. At the same time, quantum mechanics insist that the original information must remain intact in some form. This opens up a disturbing possibility: two versions of the same information, one inside the black hole and one smeared across the event horizon, and that would break the rules. In the real world, cloning would make it impossible to understand quantum computers, encryption, and even the idea of cause and effect. Imagine being able to copy the state of a basic particle or a quantum key. You'd weaken information security and make it possible for paradoxes to happen. Since black holes seem to be able to do this, either quantum theory isn't complete, or we have the wrong idea about what a black hole is. A number of proposals have been put forward. One is the complementarity concept, which says that no one person can see both copies of the data at the same time. For someone outside the black hole, the information never really comes in. It's stored on the horizon and slowly spreads out through Hawking radiation. For someone who falls in, the knowledge keeps going inside and is lost in the singularity. Both worlds are real, but no one can be in both of them at the same time. This view gets around the problem of cloning by changing what it means to know a state based on your point of view. Then there's the more radical approach. Maybe the information never enters the black hole at all. The firewall hypothesis proposes that a searing wall of energy burns up incoming data just outside the horizon, preserving information but destroying the notion of smooth passage into the black hole. In this view, the idea of a gentle fall across the event horizon is a myth. Reality is shredded just before you ever get there. Again, no duplication, just annihilation with memory preserved. The hologram concept may, however, offer the most interesting answer. If a black hole's three-dimensional volume can be explained by a two-dimensional surface theory on its edge, then information might not be copied after all. It might just be shown in two different ways. You're not seeing two different things. You're seeing two sides of the same thing, like looking at a 3D item from two different points. In this way, quantum theory, relativity, and the no-cloning theorem would all be saved. The problem of cloning won't go away. What happens when two black holes join together? Do the information contents of two event horizons merge, cancel, or strengthen when they meet? What about Hawking radiation? Does it carry only scrambled pieces of the original, or does it carry exact copies? If scientists ever make devices sensitive enough to decode Hawking radiation, will they find duplicate bits of data that were sent out before the black hole went away? The black hole as a quantum computer. Not only are black holes huge pits of gravity, but they may also be the universe's most powerful machines. In a very specific scientific way, not as a figure of speech. Some researchers, who are on the cutting edge of theoretical physics and quantum information theory, say that black holes might be able to handle information like a quantum computer. Black holes might not just store the information from the things they eat. They might also calculate with it, changing it, scrambling it, and maybe even solving problems that humans can't solve. It begins with the idea that black holes have entropy, an astronomical amount of it. The Bekenstein-Hawking formula links a black hole's entropy to the surface area of its event horizon, measured in Planck units. This implies that every tiny patch of that surface encodes a bit, or more accurately, a qubit, of information. When matter falls into a black hole, its quantum state becomes part of this sprawling, dynamic boundary. But that data doesn't just sit there. It evolves. And evolution is governed by the same kind of unitary operations that define quantum computation. From this point of view, the information dilemma is completely different. Black holes are no longer seen as places where information goes to be lost or even just stored. Instead, we think of them as places where information is processed. They take in quantum information, change it in complicated ways, like quantum logic gates, and then send Hawking radiation the results. If this is true, black holes aren't just storing data, they're also using it to do math. The Hayden-Preskill protocol gave the idea a big boost. It was a thought experiment that showed a black hole could start releasing new information amazingly quickly. As long as it's already very connected to information it has already released. This suggests that black holes work like scramblers, which are tools that quickly mix data so thoroughly that even a small output can tell you a lot about the whole input. This is similar to how a good encryption method or quantum circuit works. This leads to an unexpected intersection with complexity theory. Some theorists propose that the longer a black hole exists, the more complex the quantum state of its horizon becomes. In this view, black holes are complexity engines, evolving towards states that are nearly impossible to reverse, despite being unitary in principle. This could explain why, even though information is not lost, it's so deeply scrambled that recovering it is practically impossible without exponentially advanced tools. The effects are very serious. Does it seem possible that the world is a form of quantum computing? Are black holes the computers that are quietly running cosmic code? Could we read the information encoded in Hawking radiation if we knew their computer language? It would be like solving the final equation of life. Some researchers are already working hard to make this dream come true. Some theoretical models, such as the SIK model and ADAS CFT duality, look at black holes as quantum systems in the real world. Quantum modeling and tensor networks experiments try to model these systems on very small levels to see if they can copy the entanglement structures we think exist at the edges of black holes. Firewalls versus Fuzzballs versus Freefall, the battle for the interior. People have very different ideas about what lies beyond the event horizon of a black hole, and there are puzzles that make the very foundations of physics seem unstable. As viewers, we've usually thought of the event horizon as a smooth transition. If you fall in and somehow survive the gravitational waves, you'd go right through to the black hole's dark heart. Quantum physics doesn't like that story, though. It says that data must not be lost. So, 3 different ideas about what's inside a black hole have come about: fences, fuzzballs, and freefall. Each one gives a very different picture of what really happens when something goes through the black hole's edge. What does it feel like to be inside a black hole? This is the question that all of them try to answer. First, let's look at the most dangerous option: fences. The firewall theory says that there is a wall of high-energy particles right at the edge of the event horizon instead of a smooth one. This is thought to explain the black hole information paradox. Any things or people that fell in would be quickly destroyed. The AMPS paradox, named after Almhiri, Marolf, Polkinski and Sully, gave rise to this idea. It said that keeping quantum unitarity and not losing information comes at a terrible cost. Einstein's equivalence principle breaks down. If there are fences, then the most important idea in general relativity, that nothing special happens at the horizon, is broken. You wouldn't just float past the event horizon. You'd hit a quantum death trap. Now consider fuzzballs, a concept rooted in string theory. According to this idea, black holes aren't empty voids with singularities at the core. Instead, they're made of tangled, vibrating strings, entirely filled with quantum fuzz. There is no traditional interior, no singularity, and no event horizon as we usually understand it. Rather, all the mass and information of a black hole is spread out across this tangled mass of strings, and what appears to be an event horizon is just the outermost layer of fuzz. Nothing falls in because there's no in. You hit the fuzz and merge into its structure. Fuzzballs preserve information not by encoding it on a horizon, but by never allowing it to fall in to begin with. Then there's freefall, the classic view inspired by general relativity. According to this picture, the event horizon is completely benign for the infalling observer. You pass it without noticing anything unusual. From your perspective, gravity intensifies, time distorts, and you eventually spiral into the singularity. All the mysteries, firewalls, fuzzballs, information puzzles, are either irrelevant to your journey or only arise when viewed from outside. This model defends the idea that Einstein's equivalence principle remains intact. Locally, the laws of physics don't betray you, even when you're falling into one of the universe's most extreme environments. How do we choose the right view? That's the real fight, and it's still going on. People who support barriers say that without them, unitarity and quantum theory fall apart. The fuzzball camp says they fixed the problem by coming up with a new way to think about black holes. Freefall supporters, on the other hand, think that firewalls are too extreme and that the problem comes from trying to mix ideas that don't go together too literally. At least not yet. None of these ideas have been proven by experiments. We can't get near enough to a black hole to send a probe in and hear what it does. But evidence on gravity waves from black holes merging and better models of Hawking radiation may tip the balance in the long run. For example, if we find echoes after black holes merge, slight changes in spacetime that don't fit with what we know about general relativity, they could be signs of quantum structure at or near the event horizon. That might help filters or fuzzballs work better. Another angle comes from quantum entanglement. If Hawking radiation is entangled with its source, and new radiation is also entangled with past radiation, you eventually reach a contradiction known as the monogamy of entanglement. Resolving this is what gave birth to firewalls in the first place. But string theorists argue that fuzzballs already resolve this contradiction naturally. There's no need for entanglement across a horizon if there's no traditional horizon to begin with. Black holes in extra dimensions. What if black holes aren't what they seem to be? What if space is bigger than we think? That's the idea behind one of the most daring and strangest theories in theoretical physics, that there are extra levels of space. Everyday life takes place in three directions of space: left to right, up and down, and forward and backward. But some of the most advanced models of physics, like string theory and M theory, say the world has more. 6 or 7 secret dimensions might be rolled up so tight that we don't even notice them. And if these dimensions exist, black holes, which are the most extreme gravity labs we have, might act in completely different ways in them. One of the earliest signs that extra dimensions could affect black hole physics came from the so-called brain world scenarios. In these models, our familiar universe exists on a three-dimensional membrane, or brain, floating in a higher dimensional space known as the bulk. Gravity, unlike light or matter, can leak into these extra dimensions. That means black holes might not confine their mass and curvature to our 3D slice of reality. Their gravitational influence could stretch deeper into the hidden bulk, changing how they form, grow, and even evaporate. In extra-dimensional space, the very shape of a black hole could change. Instead of being perfectly spherical or ring-shaped, like a Kerr black hole, higher-dimensional black holes could resemble bizarre objects such as black strings or black brains, elongated, stretched-out forms extending into unseen directions. Some theories even propose toroidal black holes shaped like donuts. These shapes are more than just curiosities. They dramatically alter the math of space-time curvature and could even make black holes unstable in ways we'd never expect. In higher dimensional models, black holes radiate differently. More dimensions mean more channels through which radiation can escape, speeding up the evaporation process. A microscopic black hole created in a high-energy collision, like those at the Large Hadron Collider, might last mere fractions of a second before disappearing in a flash of particles. That's why some physicists once thought the LHC could create tiny black holes. Not dangerous ones, but evaporating ones that could reveal the fingerprints of extra dimensions. But how would we actually detect such black holes, or the existence of extra dimensions through them? One method might involve gravitational waves. Black hole mergers, like those seen by LIGO and Virgo, emit ripples in space-time. If extra dimensions exist, the structure of these waves might subtly deviate from predictions made by 4D general relativity. We might see additional ringing modes or energy leakage into the bulk. So far, we haven't detected those signs, but our instruments are improving, and future detectors like LISA could probe these possibilities more deeply. Entropy and thermodynamics give us another view. Normal general relativity says that the entropy of a black hole is equal to the size of its event horizon. The ratio of surface to volume changes in higher dimensions, though. The rules of entropy scaling don't work as they should and change in strange ways. Some scientists think this could help us understand some of the most puzzling things about quantum gravity, like why information might stay the same, how black holes store information, and how space-time geometry forms from entanglement. The ADES-CFT correspondence is an interesting idea that came about from thinking about space-time outside of dimensions. It is a mathematical symmetry where a gravity theory in a higher dimensional space, anti-de Sitter space, is the same as a quantum field theory without gravity in lower dimensions. This holographic principle says that quantum interactions on a border in a lower dimension can fully describe black holes in higher dimensions. Saying that a 3D object can be fully recorded on a 2D surface is the same thing. This idea changes how we think about space, mass, and even reality itself. Extra dimensions might also allow for entirely new classes of black holes, such as those formed not from collapsing stars, but from the geometry of space itself. These topological black holes could be stable in ways we don't yet understand, and might even contribute to dark matter. If they exist, their gravitational influence could be scattered throughout the cosmos, unnoticed because their effects stretch across dimensions we can't observe directly. Cosmic chords. Could black holes be musical instruments of space-time? What if the world is like a symphony, and black holes are the deepest and strongest instruments? There is real science that says black holes vibrate, ring, and echo in ways that sound a lot like musical instruments. This may sound romantic or silly, but it's true. These are not metaphors. They are real measured mathematics effects that come from the way space-time is put together. What's more, if we learn to pay close attention, these cosmic chords might become one of the most powerful ways we know how reality works. The first time humanity truly heard a black hole was in 2015, when LIGO detected gravitational waves from the collision of two black holes. The resulting waveforms, when converted into sound, produced a rising chirp, a literal echo of the final moments before the two merged. But beyond that chirp lies a subtle and complex aftermath, a phase called the ring down, where the newly formed black hole vibrates as it settles into a stable shape. These vibrations are called quasi-normal modes, and they are the black hole's natural frequencies, just as a bell rings at specific pitches depending on its size and shape. Based on its mass, spin and charge, each black hole has its own unique set of quasi-normal modes. The way space-time curves around black holes makes it seem like they have their own musical key. And just like you can tell what kind of instrument it is by its sound, scientists can figure out what black holes are made of by looking at these ringing patterns. This is a part of black hole spectroscopy, which is quickly becoming one of the most important areas of astronomy. We can prove or disprove Einstein's general theory of relativity with unprecedented accuracy if we can find multiple modes in a single event. We might also find new physics hidden in the harmony. But the music could go even further. Some theoretical scientists think that these quasi-normal modes might be important to how black holes process and distribute information, not just for test purposes. You can think of black holes as thermodynamic things with entropy and temperature. The way they move could represent the data they hold. So black holes might not only sing as they die, but also as they remember things. Harmonics of gravitational waves. There is a basic tone and then a number of overtones on a piano string. It's possible that black holes' gravitational wave signs show harmonics. These overtones could show up when there are very large differences in the masses of the two objects merging, or when the collision's geometry bends space-time into stranger shapes. Finding these harmonics could lead to the discovery of deeper patterns in space-time, possibly even the signs of extra dimensions or quantum gravity. But black holes may not be limited to playing the aftermath of collisions. Some researchers speculate that rotating black holes, surrounded by disks of infalling matter, might generate continuous vibrations, similar to how a bow drawn across a violin string creates a sustained tone. These potential spacetime oscillators could emit low-frequency gravitational waves indefinitely. If so, they might act like massive cosmic tuning forks, resonating across the universe for billions of years. There's also a radical idea that ties this all together: the notion that the universe itself may be fundamentally musical in nature. In string theory, all particles and forces arise from tiny vibrating strings. The frequency of a string's vibration determines the kind of particle it represents: massive, light, charged, or neutral. In this view, black holes might represent the deepest, most intense vibrations of these strings, super resonators where quantum and gravitational forces blend into one. Their ringing is not just an accident of physics. It's a window into the deepest structure of reality. Could it be that by mapping the vibrations of black holes, we're tuning into the sound of the universe thinking? Could gravitational wave astronomy evolve into a kind of cosmic acoustics, where listening becomes a new method of discovery? If you've made it this far, good job. You made it through the theory dive into the universe's most mysterious things. Black holes are not the end of the story. They are where the most important questions in science come together. They can be anything from eternal voids to quantum gates, from vibrating fuzzballs to echoes of cosmic memory. It gets stranger as we learn more about it. With the help of math and light, the next generation of cameras, quantum theories, and gravitational wave detectors may be able to open up the inside of black holes. There are edges where reality breaks, time folds, and space sings that you want to keep chasing. You're in the right place. Subscribe for more deep dives into the unknown, and click the bell to make sure you never miss another one. We'll be waiting here, just past the edge of what we know, where science meets wonder and interest turns into gravity.